Okay, Jonathan. If you are available, we can start. The students are in the room. Your microphone is off.
Hello.
Okay.
Can you hear me?
Yes, very well.
Okay. Hello, everybody. Good afternoon.
Good afternoon, Jonathan. I'm pleased to introduce you, Jonathan Erez, from the Hebrew University of Jerusalem. And Jonathan is one of the authority in the field of geochemistry. And we are honored to host him in our teaching week as a closing lecture. Okay, we'll talk a lot during this week of biomineralization, some aspect of geochemistry. We had, as I said this morning, Jeb Gandorp, Frederic Maren, and this morning we have Damir Krali, and now you are going to close this section. So welcome. Jonathan, the stage is yours. Thanks.
Thank you. My main research field is biomineralization, but because there have been so many lectures on that subject, I will not talk about biomineralization, but instead I will talk about chemical and biological oceanography and try to introduce an introduction to marine biogeochemistry. So the first lecture will be on the ocean basins, element cycling, and the thermohaline circulation of the ocean. Then I'll talk a little bit about biological oceanography, nutrients, oxygen, productivity, etc. And then I will talk about the global carbon cycle and carbonate chemistry in the oceans. And finally, if we have time, I'll talk a little bit about coral reefs and how they survive in today's ocean. Okay, so 2/3 of the globe is occupied by the ocean. And that is a very lucky situation because the chemistry of the ocean is relatively constant, and the environment of the ocean is much more uniform compared to the environment on land. And therefore, we can make relatively few measurements and get good information. So if we look at the oceans and we add to it the influence of humans, at the beginning it was almost impossible to see anything. But today we have a very large increase in CO2, we have species extinction, we have huge human population, and we have a very large increase in nitrogen fixation compared to what we had before humans started to influence our globe. And so I'm going to talk about the ocean in relation to its vertical dimension and also mention a little bit about how the ocean basins were formed. So we have the lithosphere, which is that solid part of the section. Do you see my cursor?
Yes.
Okay. Then we have the hydrosphere, which is the oceans, and we also have some hydrosphere on land. We have the atmosphere, which is the air above us, and we have the biosphere, which is all the organisms that live everywhere and influence this system very strongly. And it's also influenced by the system. So we are going to talk about various phenomena that are connected to this system. We have a cyclic phenomena, which is orbital cycles, day, night, seasons, lunar cycles, Milankovitch cycles, glacials, interglacials. So these are associated with climatic cycles that can be also much longer time. We have geological and geochemical and biological cycles. And at the same time, we have vectorial processes. Some of the vectorial processes, of course, are the creation of the universe, which are about 14 giga years. Then we have a segregation of the elements of the Earth, which is the evolution of our own unit, which is 4.5 giga years. And then biological evolution, which is maybe 3.8, slightly more giga years. And then we have man and its influence, which is only 2 mega years, which is 2 million years. The units are given here below. And we are going to talk about cycles. So everything in our system is cycling. We have reservoirs and we have fluxes into the reservoirs and out of the reservoirs. And within the reservoirs, we have processes. So a very good example of that would be the water cycle, which I'm going to show you next. And if you look at the water cycle, let's look, for example, at the ocean. So the ocean has a huge amount of water. The units here are 1,300,000 kilometer cube. Okay, these are very high numbers. For example, the evaporation from the ocean is only 426 units compared to 2,300,000. Okay, and most of the evaporation is giving rain over the ocean, but small part of it, 40% of these units is falling on land. And this gives us all the water cycle on land, that is snow and rain and rivers and lakes and groundwater. And because it is a cycle that everything has to come back. So about 386 units are falling back onto the ocean as rain. And then about 40 units which fall on land come back to the ocean via rivers, as you can see here, which is 38 units. And then 2 units come back as a groundwater reflux. So if we take that cycle, we can calculate a few numbers based on that. And for example, as I said, this is the volume of the ocean in terms of 1,000 kilometers squares. And the evaporation rate, as we talked about it before, it's roughly 430. And therefore, the residence time of water in the, in the ocean is about 3,000 years. Would you believe it that if we would have left the ocean only to evaporate, then within 3,000 years, it will be empty of water. It is quite surprising to see how large is this process. Water on land are total 16,000 of these units. And if we look at flow into the ocean, then the residence time of water on land is only 140 years, much shorter. And if we think about the ice age, then during the glacial, we took off the ocean about 40,000 of these units. And the ocean became therefore lower by 120 meters during the glacial time. And all this water accumulated as ice in the poles and on land. And if we look at groundwater, then the residence time of groundwater is fairly long. It's about 8,000 years. So this is showing you how we can use fluxes and reservoirs to calculate residence times, okay? Similarly, we can look at the nitrogen cycle. In this case, I'm looking at the nitrogen cycle in the ocean, and I'm not going to go over all of them, but it is important to say that we talk about fixed nitrogen, and therefore it's being fixed as ammonia from the atmosphere, and then it goes through many changes, and therefore we get uptake of nitrate into particulate organic nitrogen, and that one is recycled back by microbes all the way back to nitrogen by denitrification that goes back to the atmosphere. And the nitrogen cycle is extremely important for life in the ocean, as we will see later. Okay. And finally, we will talk a lot about the carbon cycle, because the carbon cycle is the one that we are now perturbing very strongly. And I'm not going to talk at the moment about the carbon cycle, just to show you that we are burning fossil fuel. It accumulates in the atmosphere, and there is strong exchanges between the atmosphere and the land ecosystem, and also very strong fluxes between the ocean and the atmosphere. But in terms of sizes, the size of the atmosphere is relatively small, about 750. This is from quite a few years before, but today it's about 850 probably. But the ocean has about 40,000 units, which are gigatons of carbon. Note that I'm talking about carbon and not carbon dioxide. Okay, carbon is only molecular weight 12. Carbon dioxide is molecular weight 44, and therefore people confuse the issues. If we talk about carbon, then these are the units. If we talk about CO2, then you have to multiply everything by 44 divided by 12, which is about 3.5. Okay, so here is the very well-known Killing curve. Killing is a scientist who worked in Scripps, and he started to measure in the late 1950s. He started to measure the CO2 concentration in the atmosphere, and discovered that it is actually going up very, very quickly. And then we have these seasonal cycles between fall and spring, and in the northern hemisphere mainly. And we will talk a lot about the killing curve as we go along. As a result of CO2 increase, most scientists believe that the global warming that we are observing is connected to the CO2 increase, because CO2 is a greenhouse gas, and the global warming is therefore associated with CO2 increase. And many, many scientists and even economists are now thinking that we need to really start to lowering the CO2 in the atmosphere in order to stop global warming and climate change. And just to show you what was the CO2 concentration in the last 1,000 years, so you can see here, it was about 280 parts per million. We call it ppm by volume. Okay, so as you can see, for about 800 years, it was more or less constant. How do we know about it? Well, we know about it very well, as I'll show you later, both from bubbles of ice that are trapped in ice, and also from several other proxies. And starting at the 20th century, we start to observe an increase in the CO2 concentration. And today, this is not even up to date. Today, we are at 425 ppm. So it's a huge increase in the CO2 concentration. And if we want to compare it to some cyclical phenomena, as we mentioned before, we can compare this CO2 of the last 1,000 years to the record of the last 300,000 years. And this is all coming from little bubbles of air that are trapped in ice. It started in Antarctica, and later on, part of it was also done in Greenland, but mainly in Antarctica. And what you can see here is that the CO2 of the air that is trapped in the ice shows CO2 concentration of about 280, going down during the glacial to about 180, and again 280, 180, 280, 180, and then came to our time. It should have been 280, and by now it is, sorry, I don't have it here, but by now it is about much, much higher, about 425, and we will talk about it later. The glaciers and the interglacials, as you can see here,
Jonathan,
are, yeah, yeah.
your screen is out. Please share.
By now, it's okay?
No, okay.
You need
Okay?
you need to share it again.
Okay, sorry. Yeah, I didn't know that. Okay, just a second then. Oh, wait a minute, because I don't have the.
When you said that I don't have it here, then you touch something and you change.
Okay, yeah, here, I'll share it again. Okay, here it is. Sorry. Do you see it now?
Yes.
Full screen.
Okay.
Put it in the
Jonathan,
Put
wait
it
a second.
Screen. Yes.
Okay. So I talked about the glacials and the interglacial cycles. This is about 100,000-year cycle, and we know it very well because of the ice cores and also from deep sea cores in the ocean. And at that time, we were only having 3 or 4 cycles, but now we know that we had at least 10 to 12 cycles like that. And over the last 2 million years. And this is a cyclic phenomena that is connected to the parameters of the globe, which are shown here. You can see here the shape of the rotation of Earth around the sun, which is elliptical, and it can be more elliptical or more circular with a frequency of about 100,000 years. We can change the tilt of the Earth at a frequency of about 40,000 years, and we can have a precession of the tilt with a frequency of about 20,000 years. So if we put all of them together, we get a cycle which is about 100,000 years that dominates the climate on Earth. And this is what led us to glacials and interglacials. So here we look at the Earth today. And if we look at the Earth about 18,000 years ago at the height of the glacial, then you can see that most of North America was covered with ice. Good parts of Europe were covered with ice. And of course, the poles were much richer in ice. And especially in Antarctica, we had a thick cover of ice, much thicker than we have today. And as a result of all that, the sea level went down by about 120 meters globally. Okay. Okay. Now we can talk about some vectorial processes. These are processes that go unidirectional. So we started to talk about the generation of the universe and then segregation of the elements within the Earth, biological evolution, and then man's influence, which is ongoing and extremely increasing. And when we talk about segregation of the elements on Earth, then we know that we are living on a very, very thin crust that you can see here. The crust is only 0 to 40 kilometers, very, very thin compared to the diameter of Earth, which is about 6,400 kilometers. And then below the crust, we have the mantle. And below the mantle, we have the core, the liquid core, and then the solid core. And all this is actually determined from seismic waves and models and theories, because nobody is able to penetrate even into the mantle. We still do not have any drilling that reached the mantle. Okay, at the moment, the deepest drill in the ocean is about 1,200 kilometers, 12,000 kilometers, 12,000 meters, sorry, and that's it. So we know very little about what is going on inside. All what we know from rocks, from minerals, and of course, the deepest of all are the diamonds. Diamonds are coming from a depth of about 100 kilometers. So this is the maximum that we have, okay? Life is again a process that started to evolve sometimes, and it's going on and evolving continuously. So what you see here is just a nice presentation of the evolution of life. It started very, very modestly, some about 4 billion years ago with some microbes and stromatolites about 3.8 billion years ago. And then it went on and on and on. And only about 540 million years ago, 543 to be accurate, we are starting at the Cambrium. In the Precambrium, we had just a few tenths of million years, other organisms that today we don't have. And then we had the trilobites and the big explosion of the Cambrium with lots of organisms that we even know today, like nautilids and crustaceans and fish, and eventually all the Carbon period and the Permian, the Triassic with all the large reptiles and that you see here very nicely, all the way here in those four panels. And they all died at one point when a meteorite hit Earth. That was at the Mesozoic, Paleozoic boundary. Sorry, I'm confused. All this was in the Mesozoic, and then they all died later. And the biggest event that happened later was at about 65 million years ago when the Cenozoic era started, and that was when a meteorite hit the Earth and caused apparently a very strong several years of winter because of the dust and of the volcanic activity that evolved. And since then, we have the evolution of life as we know it today, the last 65 million years in the Cenozoic era. And evolution, of course, continues, and man's influence is very strong. Okay, so this is actually the same. If you just want to look at the geological timescale, the geological timescale was divided according to the fauna, according to the organisms and the fossils that are found in the fossil record. And therefore, as you can see, the name is Paleozoic, Mesozoic, Cenozoic, and the Cenozoic is divided into Paleocene, Eocene, Oligocene. All this means faunal composition that is more and more similar to what we have today, which is the Holocene, okay? And I will not continue to talk about it, except to mention that in the last 2 or 3 million years, we have human evolution, and that is, of course, a very short time period, but of course, with huge influence on what is happening on Earth. So here is the evolution of life. Started about 3.8 billion years ago. What we have at that time is the stromatolites, which are algal precipitates that are associated with, apparently, with photosynthesis and precipitation of calcium carbonate. This is called stromatolites. Most people would believe that this is already indication of life. Later on, some first aerobic bacteria evolved, and then about 2,000 million years ago, we had the first eukaryotic cells, which are more developed and are actually symbiotic between prokaryotic cells. And then just before the Cambrian, we already had multicellular organisms. exoskeletons, biomineralization, and then and then we had the Paleozoic, which is well indicated by fossils that are found everywhere, and the age of reptiles, and finally the Cenozoic. Okay, so this is an ongoing process that is continued to develop. And I think I will leave that. It's actually the same. But the important thing here is to see that the number of families and marine animals went through fluctuations. Sometimes there was an evolution and increase in the number of families, and then there were extinctions, like you can see here at the Permian, at the end of the Permian, after the Carbon period. And then we had again a strong evolution, and then the KT boundary 65 million years ago, and then the Cenozoic. Okay. And here I would like to mention, since we started to talk about the evolution of the rocks and the crust of the Earth, we need to talk about a very interesting hypothesis that was put forward by a scientist called James Lovelock. It's called the Gaia hypothesis. I want to mention it because the Gaia hypothesis is actually trying to explain the evolution of Earth in view of the beginning and the evolution of life. And the hypothesis of Lovelock was that life itself is modifying the environment in such a way that it can continue to exist. There were many arguments about this Gaia hypothesis. Some people think it's right. Some people think it's fake, not fake, but not right. I would say it's a great idea to think about, but it is certainly very difficult to prove that life itself has modified the environment in such a way that it will continue to exist. Okay, but that was the hypothesis, and for many years it gave many people good ideas to look at life. Okay, for example, one thing that evolved during the evolution of life is the concentration of oxygen. When Earth started about 4.5 billion years ago, there was no oxygen, no free oxygen in the atmosphere. And on the other hand, the CO2 concentration was very high. Slowly and slowly, oxygen started to accumulate. And of course, it accumulated mainly because of photosynthesis. Because photosynthesis takes water and makes out of it organic matter and oxygen. And therefore, the oxygen started to increase. It did not increase continuously for a very high rate, mainly because a good part of the oxygen was taken to oxidize continental rocks, and later on to oxidize different minerals. But at one point, which is about here, about maybe a little bit less than 2 billion years, oxygen started to accumulate in the atmosphere. And at the Cambrian, we think that the oxygen in the atmosphere was already at a concentration of about 20%, which is what we have today. Okay? And at the same time that I'm sorry about this figure, but it goes the opposite, okay? This is 4.5 billion years ago, and this is the recent in this side, on the left side. So you can see that at the same time that the oxygen went up, CO2 went down. While today we have only several hundred ppm of CO2, in the Cambrian, we had concentrations that were 3 orders of magnitude higher. And you can imagine that the greenhouse effect was much, much stronger than today. And this is explained how did the ocean did not boil. That is because the luminescence of the sun was much lower than today. This phenomenon is called the young faint sun. And to compensate for the for the lowest radiation of the sun, we had higher concentration of CO2. But that CO2 was taken for photosynthesis, and slowly organic matter accumulated and the CO2 concentration went down. So this is the big picture of how life affected our system. So you can see it here, CO2 goes down and oxygen goes up. And the whole thing is, of course, bringing us to the Phanerozoic, which is 540 million years ago, which is our time. Okay? That's the same, so I'm not going to repeat on it. The CO2 decrease is shown here more dramatically, and there were also fluctuations within the Phanerozoic. And what you see here is the CO2 concentrations that were still higher and lower and still higher and lower. And the correlation between CO2 and temperature is very, very clear from the fossil record, especially during the Cenozoic. So we are quite certain that what we see today as global warming is indeed caused by CO2 because of the fossil record. Okay, so now let's look a little bit at the ocean basins. And just to break the talk, here is a few pictures. You see the movie?
Yes.
Yes.
So this is how the ocean floor is looking. It's not flat at all, as you can see. Of course, it's vertically exaggerated. But you can see here, this is the North Atlantic ridge, which is the longest ridge on the globe, 16,000 kilometers. Eighty thousand kilometers. And here is Iceland, which is part of the Mid-Atlantic ridge that is above sea level. And you can see here the, so I think that's it. Okay, sorry. Okay, so what makes this ocean floor the way it looks? The most important process was discovered only about some 50, 60 years ago. When I was a graduate student, that was a new hypothesis that was just put forward, and there were lots of arguments if it's right or not. But today we all know that we had something which is called plate tectonics. Plate tectonics is happening because of the circulation within the mantle. So we have a strong currents that bring warm material towards the surface, and in other places we have downgoing colder circles, and this makes volcanoes, and the volcanoes are, of course, making our atmosphere to begin with, because it brings water, it brings nitrogen, hydrogen, CO2, oxygen. Almost everything that we find in the atmosphere comes from volcanoes. And the volcanoes are concentrated in the mid-oceanic ridges. As you can see here, the North Atlantic ridge and the Pacific ridge, the South Pacific ridges, and the Indian Ocean ridges. And so as people started to look at this, if you looked at today's topography, you can see that we have very short area of the Earth with very high elevation, which is the Everest, for example, okay, above almost 9 kilometers. And then we have a very wide area, which is close, more or less close to sea level. Then we have a slope, and then we have the deep ocean basins, which form the ocean. And within the deep ocean basins, we have the ridges that separate between the plates. And the whole thing is therefore can be separated into plates. And these are the plate boundaries you can see here. So the plates are defined as big blocks that contain both oceanic part and continental part. And so, for example, here we have the plate of Africa, which is separated from the plate of America with the North Atlantic Ridge, South Atlantic Ridge, and then you see all the plate boundaries. Some of them are opening. So the opening of the plates is done by volcanic activity. And of course, because we have a globe that is confined in its volume, it doesn't change its volume, then if it opens in one location, then it has to be consumed in another location. And therefore, we have all these plate boundaries here that are marked in yellow that are subduction zones where the plates go underneath each other. And it can be continental plate, it can be oceanic plate, but the important thing are the boundaries between the plates, and you can see them here. So here, for example, we open in the ocean, we open a plate, and you can see that the magma is coming up from the from below with lots of heat, and it opens up. And then in other locations, the plate is going underneath another plate, and then we have other phenomena, okay? So I don't want to expand on it, but if we have here the ocean, for example, this is the oceanic plate, Indian Ocean plate, and you can see here the volcanoes that is coming from the mid-oceanic, mid-Indian Ocean ridge. So we have volcanoes underwater, and because it opens here, it has to close somewhere else. And right here we have India going underneath Asia, and this is causing the big Himalayan mountains. Okay, so this process of plate tectonics, as I said, it's a relatively new hypothesis, but it is very well founded, and one important tool to demonstrate that indeed it occurs are the magnetic anomalies that were found parallel to the ridges. These magnetic anomalies were later dated very accurately because people drilled into the different ocean floors and dated them by uranium and K-argon ages. And therefore, we know that what you see here are really the ages of the seafloor, as you can see here by the scale. And as you can see, the oldest seafloor that we have is not more than 180 million years. So all the seafloor that we have in today's ocean is relatively new. And the old parts are already consumed in the zones where it is going down, in the subduction zones. So if we want to look at the history of it, then some 200 million years ago, all the continents were more or less together, and there was a big ocean that was almost free of land. And the land mass was called Pangea. You can see the Africa and Americas and part of Asia. And then the Atlantic started to open, and the Americas were shifting away from Africa and Asia, and it continues until present, where today you have the following picture. And of course, this is only part of the picture, just to show you how it happened. And we know this very, very accurately, both from the magnetic anomalies and from the drillings that were done to date the magnetic anomalies. Okay, so the rate of motion are not negligible. Ocean spreading can be 10 centimeters per year. That is not negligible at all. It's measurable. People can measure the movement of the continents using GPS today. Slow moving rates are 3 centimeters per year, okay? and therefore we know it very well. And to summarize the whole thing, I want to show it on view of the um, chemistry that results from all these. So first of all, plate tectonics made the topography of the ocean and the topography of the land. So we have land masses which are high, we have the ocean basins which are deep, and we have a different thickness of the crust. And this process is ongoing. CO2 is released, and it is also making calcium carbonate rocks, which are dissolving. Lots of silica is dissolving, silicate minerals, the calcium wollastonite here is dissolved by CO2 and producing calcium bicarbonate and silica. And then calcium carbonate dissolves and precipitates. Silicate rocks continue to be eroded, both on land and also underneath the ocean. And there are, of course, other details which I'm not able to talk about right here. Okay. Good. So here we talked about the topography. This is what made the topography, and I think I showed you that one already. And then we can go into the rock cycle, the big rock cycle, which is with a residence time of about between 100 and 150 million years. So we have the igneous rocks that come from the mantle. We have the hydrosphere, we have the atmosphere, we have the biosphere, and all these are making biogenic deposits and create sediments. And all the biogenic deposits and the sediments make sedimentary rocks, and all the sedimentary rocks eventually become metamorphosed in organic processes that I described, for example, in the Himalayas. And then some of these rocks and everything can be melted. This is called anatexis, and it goes back to be magma, the primary material, which then comes with volcanism again and makes again igneous rocks, interaction with the atmosphere and the biosphere. And that cycle is the big geological cycle that is driven by plate tectonics. And the cycling time of this cycle is about 150 million years. Okay. As a result of all that, we have the chemical composition of the ocean. So what you see here are the concentrations of different elements, and what you have here is the residence time of these elements. So as you can see here, the most abundant elements in seawater, of course, are sodium and chloride. Then we have all the magnesium, sulfur, boron, and calcium, which have much lower concentrations. Note that this is a log scale, okay, logarithmic scale. And so these are 1 orders of magnitude lower than the sodium and the chloride. And then we have all the minor elements that you see here. And of course, all the very low concentration elements that are very, very low concentrations. Many of them are traces, but we can measure them. And they all exist in seawater. You can find in seawater almost the entire periodical table, okay? And the residence time of these elements depends, of course, not only on the processes that produce them and consume them, but also on the concentration. So if the concentration is very low, then the residence time becomes very low, as you can see here, 10 to the minus 12 years or something, or things like that, okay? So you have a very short, this is the oceanic steering time, this is a water residence time, as we talked about it before, and the elements here have very, very low residence times, okay? About 100 years, 1,000 years, and so, etc. Sodium, on the other hand, is about 1 million years, 100 million years residence time, and chlorine is even larger. Okay. Okay, so the next, we are going to talk, we talked about the general chemistry of the whole system, and next I'm going to talk a little bit about the circulation of the ocean, because as I said, the ocean can be considered relatively homogeneous because it is circulating very strongly, and the ocean circulation is driven by sun radiation, by the gradients between the poles and the equator, the atmospheric circulation, the Earth's rotation, as we talked about, and the Coriolis force, if you heard about it. We have, therefore, differences of temperature, salinity, ice, density gradients, and then we have, of course, tides that are driven by the movement of the Earth around the sun and the moon around the Earth. To all these forces that I mentioned above, we have to add the process of continuity. So if water move in one direction, they have to come from another direction, and therefore we have to keep everything continuous. If water are sinking in one part of the ocean, other waters have to come up in another part of the ocean. So this principle, we call it continuity. And of course, a lot of the circulation that I mentioned all above is determined also by the configuration of the continents relative to the configuration of the oceans themselves. Okay, so for example here, let's look at the temperature in the ocean. And as you can see, the temperature is warm in the equator. And of course, we have a big gradient of temperature between the equator, which can be above 30 degrees Celsius, up to 35 even, and then all the way to the poles. And right here around Antarctica, we have the lowest temperatures that we can observe on Earth in seawater, which is -1.5 or something like that. We cannot go below the freezing temperature of seawater, okay? Then of course, we make sea ice, and it is not already water, it is a solid. And so this is a picture from satellites that gives you a picture of the temperatures of the ocean. And as a result of this warming that comes from the sun, we have a very important feature in the ocean that is called the thermocline. So that is, surface water are warm, and then as we go deeper, it gets cooler and cooler and cooler until we get to very low temperatures of about 3 or 4 degrees Celsius. So this profile, for example, is in some subtropical waters. And then if we go to higher latitudes, mid-latitudes, for example, then we have a strong seasonal difference. So in the winter, we have a very low thermocline, and then in the summer, we have a strong thermocline. And in between, we have this, what we call seasonal thermocline. But if we go to higher latitudes, close to the poles, then the temperature is almost uniform from the surface all the way to the bottom. And that is, of course, what drives the ocean circulation. So if you want to look at it, for example, at the seasonal thermocline in mid-latitudes, so you can see here in August, we have relatively warm temperature, and then a uniform surface layer, and then it goes all the way to the thermocline. The thermocline is here is shown as 4 degrees Celsius. And then in August and September, it gets deeper, and later on in November, it gets even deeper, and in January, it gets very deep, up to 100 meters. So we eliminate the shallow thermocline, and we have mixing. And then as we continue the time, in March, we have almost uniform water column up to 100 meters. And then in May, we start to get a new thermocline that develops in July until August, okay? So this is the seasonal thermocline that is described here, in a section, as you can see here. And that, of course, is very important for coastal oceanography and also for the open ocean. Okay. And if we want to see a big cross section across the ocean, so this is across the Atlantic. You can see it here from North Atlantic to the South Atlantic. So this is north and this is south. And you can see here the thermocline, thermocline water, which is very shallow in the tropics and in the equator, and gets a little bit deeper in the mid latitudes. And then, of course, the thermocline disappears as we go towards the poles. That's where we have no thermocline. And because this is here, for example, in the north and also in the south. So right here, we have cold temperatures all the way from the top to the bottom. And when we have cold temperatures from all the way from top to the bottom, the water are not stratified anymore, and therefore water can go down according to their density and make the general circulation of the ocean. Before we go into that, I will only mention the atmospheric circulation. This is really something that we are not going to talk about, but it is driven by similar forces. That is a thermal gradient between the equator and the poles, and there are circulation cells that in the atmosphere, and this also is influenced by movement and Coriolis force, as you can see here. I don't want to expand on it because this is really beyond what we want to say. And this is the wind patterns that we see on the globe. And you have the trade winds, and we have the westerlies and the easterlies, and that circulation of the atmosphere drives part of the circulation of the surface ocean. And as a result, you can see here the circulation of the surface ocean. It comes as very big eddies, and some of these currents, surface currents, we are now talking all above the thermocline, okay? So this is shallow water of about 100 meter, 200 meter maximum. And we can see here warm currents, and then we can see some cold currents, as you can see here, okay? And because of the Coriolis force, let's take, for example, the Peru current, it goes up north along the continent. And because Coriolis force in the southern hemisphere work to the left, then this brings also water from below to the surface. That is why this is a cold current. Similarly, if we go here in the South Atlantic, we see here the Benguela current, which is a current that makes, again, water go away from the continent into the ocean, and that brings water from below. That is a process called upwelling. Similarly, we have the Canary current. We have the currents of in the western coast of the United States, and this is part of the main upwelling systems in the ocean that brings water from below. Why do we have to bring water from below? We have to bring water from below because water sinks down in the high latitudes. For example, here is the warm water that circulates in the ocean. This is the general circulation picture of Wally Broker. And as you can see here, water comes to the North Atlantic, to the Norwegian Sea, and it becomes, the water originally start here in the, it's not really very accurate here, I'll show you later better pictures, but it's warm and saline water, surface water, that arrive to very high latitudes in the Norwegian Sea. It sinks down and makes the North Atlantic deep water. The North Atlantic deep water go all the way here. Here it is joined by the Antarctic bottom water, which come from Antarctica, again, very cold water. And these cold water go into the Indian Ocean and continues all the way to the Pacific Ocean. and only then comes back as surface currents and goes back to its origin. And as I said, this is what we call the continuity principle, that if we have water sinking in one location, we have to have water coming up in another location. So here we have the water coming up, okay, in each one of them. And this is like a picture of how these currents go. And you can see that the surface currents, which is a Gulf Stream, actually starts here, goes into the Caribbean, and continues towards Europe, and is cooling. It's actually warming up the European land. But there in the Norwegian Sea, and part of it comes also from the Labrador Sea, it is sinking and making the deep Atlantic, North Atlantic deep water that goes into the Pacific, and part of it continues into Indian Ocean, and then into the Pacific, and then comes back. And this is only a picture. You have to, if we want to look at the details, then we are looking at these pictures. Just a minute, let me see. Yeah, I still have some 15 minutes. Okay, so this is all can be displayed on temperature versus salinity diagram. And the lines that you see here are equal density. So the density of seawater are determined, first of all, by temperature. As you go down by temperature, the water become more dense. So you can see the density here. This is 1.024. This is 25, this is 26, etc., etc. Right here, 1.027, okay? So this is really starting to be very dense. And then if we take it a certain very low temperature, if we go up with salinity, that makes the water even denser. So we have a real increase in density in this direction. And the density of seawater can be very low as 1.024 and can be very high as 1.029, okay? Because we don't want to carry all these numbers, so people always take off this density -1 and multiply it by 1,000, and we call it sigma t. So the sigma t here is 25, and this is 26, and this is 28, etc. Okay? Now, these very small differences in density make huge difference for the circulation of the ocean. And if we look at the same diagram, we can see here the Antarctic bottom water. These are the water that sink around Antarctica, and they are very, very dense, probably the densest that we have in the ocean. So this is like 1.028. And then we have the circumpolar deep current, deep water, which is slightly less dense, but makes the Antarctic bottom water. We have the North Atlantic deep water, which are less dense or almost as dense as the Antarctic bottom water, and they mix around Antarctica. And so in this way, we can separate the water masses on this temperature salinity diagram. To show you how the real data looks. So this is from many profiles in the Atlantic here, and you can see here the different colors, and on a sigma t, as I said, on a sigma t numbers 28, 27, etc. And you can see here the North Atlantic central water. You can see here the Antarctic bottom water. You can see here the Antarctic intermediate water and the North Atlantic deep water right here in this corner at this point. So you see the Antarctic bottom water and the North Atlantic deep water are almost on the same sigma t line, but the Antarctic bottom water are slightly more dense. Okay, and if you want to look at it as a cross section, this is the older presentations of this stuff. So we have here the North Atlantic deep water. It's a huge water body of water that are very dense, fill all the way to the bottom of the North Atlantic, and then as it goes south, it meets the Antarctic bottom water, which sinks around Antarctica, and here the two water masses are mixing. And in this picture, you can also see a point here, written M. Who knows what M means? Anybody knows? M is Mediterranean water, okay? It's important because the Mediterranean produces very saline water, which pour into the Atlantic, into mid-depth in the Atlantic, and eventually they make the high salinity of the North Atlantic deep water. And this is what makes this water mass so big and so important. Above it, of course, you have the water that are above the thermocline, and we have here relatively high oxygen because this water leaves the surface with a high concentration of oxygen. It's called water. And then as it ages, the oxygen gets consumed slowly and slowly and slowly. And here we get already oxygen minimum. And then we have, again, waters that are rich in oxygen because they just sank from the surface in the Antarctic bottom water. So the very low oxygen are the Antarctic intermediate water tongue that we can see here. And this is low oxygen minimum. And I will just mention how these currents look on a small movie that you can relax and look at it. So here is the Gulf Stream going up north and into the Labrador Sea and starts to become cold and start to sink down, and as a return flow, you see cold water, okay? And this is how the North Atlantic deep water are being formed, and this drives the deep circulation of the ocean, or what we call the general circulation of the ocean. Of course, it's only a cartoon. You don't have to take it so seriously, but it really represents, and there you see it goes into the South Atlantic, and in the South Atlantic it gets the addition of the Antarctic bottom water. And then, of course, surface currents are coming along the continents and making upwelling to compensate for all the water that sank. Okay, so this is really a nice presentation of the whole story. Let it finish, because otherwise it will repeat itself. Oh, sorry. Okay, so we talked about it already, and this is the same. I don't want to expand on it. What is the rate of water movement? It is relatively high. As you can see here, the units that we measure, the volume of circulation, of the general circulation of the ocean, is by a unit called Sverdrup, after one of the famous researchers who started to do this work in the 1940s. And Sverdrup, one Sverdrup is it's about million meter cubes per second. Okay, just imagine million meters cube per second, and the North Atlantic deep water is estimated to be 17 Sverdrups. Okay, it also moves, of course, heat, because as we said, if you bring warm water and they cool down, that means that you bring warm water to the north, and you can measure it by picowatts, 10 to the 15 watts. Okay, I think I will leave this. I will only mention the source of this diagram. The source of this diagram is by a fellow called Tully, 2015. He made many papers describing these circulations, especially around Antarctica, and how the Antarctic bottom water go into the Atlantic, into the Pacific, into the Indian Ocean. And if you want to learn more about the circulation, the general circulation of the oceans, this is a very good source. The name Tali, he has many papers. Okay, we finished all that, and I think, let me just see a second. You lost the picture? Do you see the picture? Hello?
Okay.
Yes, we can see.
Okay, so I will only mention that of course the topography together with the circulation gives us all the environments that we have in the ocean. We have the coastal zone, we have the continental shelf, we have the continental slope, and the deep ocean, which you see here. In the deep ocean, we have the pelagic forms, the swimmers and the plankton, zooplankton and phytoplankton and nekton that is swimming, etc., etc. Well, you work, most of you, I guess, work on the continental shelf, and therefore you are exposed to the neritic zone and the littoral zone, etc., etc. All these are environments and that are in shallow water. And I think we will take here about 10 minutes break, and then we will continue. It's okay?
Yes, Jonathan, thank you.
Okay. So at about 1650, we will continue.
Okay, thanks.
Thank you.
Not 16, it's 1550 in your time.
Yeah, thanks, Jonathan.
Okay, good.
So, Jonathan,
Yeah,
I
I
think,
can hear you.
yes, there may be a couple of questions from the students. The first
Okay.
is there are data that are indicating that the general current of the ocean is decreasing the speed.
Right.
If you have any comment, but for later. Now they're taking coffee, please.
Okay, I will say it in the next lecture. Yes.
Second one is how can we be sure that global warming now is anthropogenic if in the past the concentration of carbon dioxide changed so much?
Okay, I will answer that one as well.
Yeah, thanks.
Okay, good.
Third one is from Francesca that is eager to know what did you found with your last scan?
Yeah, it's complicated. It is not really, there aren't any special news. The instrument is not really well suited to work on topography of single polyps, okay? It is really made to work on rocks, carbonate rocks that you flatten, and usually it's a 5 centimeter by 5 centimeter pieces, okay? So when we look at the coral, it is very difficult to see because of the very high topography between the septa and the spaces between the septa. Okay, that puts the machine into giving us compositions that are not correct. But the wall, I don't know if, of the teca, you know, of the whole polyp, that one gave some information, and that information is not very easy to interpret because it depends on and how they program the information. Okay, so they sent me a whole bunch of pictures that I still did not have. That was only yesterday afternoon, so I still did not have time to really sit on it and discuss it with the person who has done it. And because he is still asking me questions, can it be that we have high concentration of whatever? But we did not see any aluminum that was abnormal, but we did see some iron that was high. But I think this is still too preliminary to say anything. Meanwhile, I saw Francesca on the iPhone. What Stefano sent me, I see that you have now a nice aluminum maps.
Yes.
Yes,
Yes.
that's for each of the elements. Because also we had very interesting lectures from Giovanni Valdré, which is the professor of the geologist that is the one that is actually the head of the EDS.
Yes.
The professor that brought the EDS in Bologna.
Yes.
The lesson is recorded. If you want, maybe have time to look at that. We can send you the link, and he's explain us, I guess, some important features on how the machine is working. And basically, I asked him if it's the relative difference in the concentration of atomic percentage are reliable, and he said, of course, he said yes, they are reliable, and that's what was a good point. And this explain also why are reliable, are trustable. And then with Jeff Kendor, we see it a bit, and he look at the raw data, Jep, and he suggests how to analyze the map, and now produce three-dimensional map. And now Francesca is producing the kind of map for each of the elements that we have in the analysis.
Okay, great. Yeah.
So that's it. That's what I want to say.
Yeah, we did two maps. We did a map of your coral, and also a map of the Stylophora. We also have the piece of Stylophora from Sharon Ram.
Okay, I'm here.
And yeah, I wanted to consult with you about it. Because this is the last piece we have, and also your coral is the one that we made the measurements. This is what was left from it. Okay, so I'm a little bit afraid to send it by the fast mail, and I thought next week I'm going to meet Giuseppe Fallini, and I wanted to give it to Giuseppe. And next time that somebody is traveling to Italy, maybe he can take this, not only that sample but all the other samples that you gave me, to take them back to Italy. I'm afraid that we will lose it because it happened to us at least twice that the FedEx was lost.
Giuseppe then is coming to Italy.
He's not coming to Italy, but he said that there are many people in the embassies that come and go.
Nell'ambasciata c'è qualcuno che viaggia spesso.
So it's up to you. If you say put it in the FedEx, I will put it in the FedEx and send it, but then I'm not responsible anymore.
No. Okay, wait a sec. I'm not want to force just listening the idea. I don't know. When you are gonna meet Giuseppe?
On Monday, I think, next Monday.
In a few days.
Yeah. He's supposed to come to our university, and we said that we are going to probably have lunch together, and I can give him all the samples. I'll pack them well and give him it's about, I have like maybe 12 samples altogether. With our corals, it's probably a few more. And I want to give it to him so that maybe he can send it with a diplomatic mail. It will be safer.
Okay,
Okay.
give it to Giuseppe.
Okay, good.
And then
Okay,
yes, we will arrange with Giuseppe. Okay.
okay. Let me see where I am. I'm supposed to be on the Teams.
Yes.
Teams, okay. I want to share. I want to share Windows, and I think I am in the second presentation. That one. Yes. Okay.
Io non ho capito una cosa.
So let me know when I can start.
Yes, okay.
Oh, teaching?
Sì.
Teaching, oh.
Sì, sì.
Stefano? Hello?
Wait, yes, I'm here, Jonathan.
When are we starting?
Yes, now I'm calling the students.
Okay.
Okay. Please, we are ready to restart Jonathan Erez second part of this lecture. Please have a seat. Thanks.
So we had two questions. One was about the global warming, and the second was about the CO2, right?
No, the second one was about the general circulation that is decreasing the speed.
Yeah, decreasing general circulation. Okay, yeah.
Okay. Now I close the microphone, so it's better for the audio. My microphone, okay. So please, Jonathan,
Okay.
stage is yours. Thanks.
Okay. So next, I'm going to talk a little bit about the factors that influence the chemical biological pump in the ocean. And when I talk about chemical biological pump, I mean what brings CO2 down to the deep ocean and what releases it back to the atmosphere. Okay, so this is just a small cartoon showing us that we have both organic carbon playing in the game, and that is taken from the atmosphere to the ocean. In the ocean, we have photosynthesis that makes organic matter and oxygen. And at the same time, we also have calcium and bicarbonate, and this causes precipitation of calcium carbonate that also sink into the bottom of the ocean. But the organic carbon pump is bringing organic matter into the deep sea and from the deep sea into the sediments, and therefore it accumulates there, or part of it accumulates there. On the other hand, the calcium carbonate is very complicated because when calcium carbonate precipitates, CO2 is coming out into the atmosphere. And I will talk about it not in this lecture, but in the next lecture, and explain exactly why precipitation of calcium carbonate is causing release of CO2 to the atmosphere, because it is not clear from first look. But I'm going now to concentrate mainly on the organic carbon pump in this lecture. Okay, so we have primary productivity in the ocean, or productivity. This is an ecological unit. We measure the rate of biomass accumulation. We can measure productivity of phytoplankton, we can measure productivity of zooplankton, and even productivity of fish. It doesn't matter. That means how much organic carbon this group is accumulating, okay? The primary production is really the beginning of it, which is the photosynthetic activity of phytoplankton. We can also have primary production by not only by photosynthesis, but also in the deep ocean, we have primary production by chemosynthesis. But this is an interesting ecosystem, but it is not very important in terms of quantity. Okay, so I will talk mainly about photosynthesis now, and this is a simple reaction. The 6 molecules of CO2 with 6 molecules of water make organic molecule and releases oxygen. So this is the simplest way to present photosynthesis. And the opposite reaction, of course, is respiration, where you take sugar and with oxygen and you make CO2 and water. Now, in the ocean, the water is not important because we have so much of it, and there is no limitation of water in the ocean. But on land ecosystems, water is many times a limiting factor for photosynthesis. And of course, photosynthesis is done only with sunlight. So we have to consider that and to see what is really inhibiting photosynthesis in the ocean, and this will become very clear next. So here is our ecosystem in the ocean. It is full of life, and all this part that you see here with the big fish and the squid and everything else is really not important, even though this is only the economical part. The most important part is right here in the phytoplankton, okay? Phytoplankton and perhaps the zooplankton, because these are the primary producers in the ocean. They make photosynthesis, and when you go to the shelf, you also have lots of seaweeds, and that is also important primary production. And we also show here the zooplankton, which is an important group because it consumes the phytoplankton, and therefore it helps to the biological pump to work and transport carbon from the surface water to the deep water. And if we look at the various modes of life in the ocean, then we have the plankton, which will be our main subject. We have the benthos that live on the bottom of the sea, and we have the nekton, which are the swimmers. So fish, whales, turtles, squid, these are the nekton. The plankton is divided into zooplankton and phytoplankton. The character of all the plankton is that it is actually carried together with the current. It cannot swim against the current. And the benthos are all the organisms that live on the bottom of the ocean. When we talk about both zooplankton and phytoplankton, we need to look mainly at the zooplankton. We have to look at the differences. There are things that are called pseudoplankton, which are not really planktonic organisms. They are benthic organisms that stick to different planktonic systems. We have meroplankton, which are larval stages of benthic organisms. We have ichthyoplankton, which are little fish. And then we have the demersal plankton, which appears only at night. They come organisms that come to the water column from the sediments. And the biggest variability in the ocean is really in sizes. People don't always think about it, but if you think about the sizes of all these organisms, then the nekton is, of course, very large. And then we have the metazoans and the protozoans and the phytoplankton and the picoplankton and the bacterioplankton and the viruses. And we go here from 10 to the -8 all the way to 10 to the -1. Okay, so it goes over about 8 orders of magnitude changes in dimension. This is very important. And often people ask why organisms in the ocean are so variable. In my opinion, this is all because of the differences in sizes. Each group is of different size, and each group is specializing on feeding on different size, and therefore the great diversity of marine organisms, in my opinion, is connected to size. Okay. So we all know that at the bottom of the food chain, we have the primary producers, then we have the herbivores, the primary carnivores, secondary carnivores, and tertiary carnivores. And of course, in FishMed, we deal mainly with larger organisms that are commercial, and humans use them for feeding. But in the ocean, what is really important is the phytoplankton and zooplankton. And let's look a little bit at phytoplankton. So here you have some algae, cyanobacteria, and other algae. We have dinoflagellates, which can be toxic. They are all unicellular. We have diatoms that are made of silica. We have more diatoms. We have coccolithophores, which are calcareous algae that are very small. I mean, such a cocosphere is only about 10 microns or so, and the coccoliths themselves can be only 5 microns or so. So they are very small. And before electron microscopy, it was very difficult to even identify them to species. And then we have, of course, the zooplankton. And the zooplankton is very important in this whole game because it transports the carbon of the primary producers into the deeper ocean. And here is a schematic that explains how this is happening. So, for example, here we have coccolithophores the coccolithophores are eaten by the copepods, and the copepods are making fecal pellets, and the fecal pellets are falling very quickly into the ocean floor. So, for example, if you would take individual coccolith, which is one of these small ones, and you let it fall to the ocean floor individually, it will take 200 years. And because the surface circulation of the ocean is only several years, then of course all the coccolith of all the oceans would be uniform. But in reality, what is happening is that all the coccolith are being eaten by the copepods, and the copepods make fecal pellets, and the time it takes the fecal pellets to reach the floor is only 2 weeks. So the fecal pellet transport or large particles transport of the zooplankton grazers is the connection between the phytoplankton and the ocean floor. This is what brings carbon from the surface to the ocean floor, and that's very important. Okay, so here examples, things that we collected in sediment traps many years ago. You can see here a fecal pellet of a copepod, and you can see here that if you increase the picture with an electron microscope, you can see that all of it is made of coccolithophores, of coccolith, okay? And these coccoliths would have never arrived to the deep ocean if not for the fecal pellet itself, okay? Now, let's talk a little bit about photosynthesis. So, of course, it's all done by the sun. The sun is giving us a very strong radiation, and this radiation is absorbed very strongly in seawater. And in fact, most of the radiation of the sun is absorbed in seawater and its particles. And once we reach a depth of about 100 meters, we almost don't have enough light to make net photosynthesis. The radiation of the sun radiation, of course, is what warms Earth, but it is shortwave radiation hitting the Earth, becoming long wave radiation, and that radiation is coming back to the through the atmosphere back to space, if not for the molecules that we have in the atmosphere that absorb this long wave radiation, and CO2 is of course one of these major absorbents. Water vapor is also very important, but we all believe that this is CO2. This is why CO2 is a greenhouse gas, and because it is increasing, we believe that this is what makes the difference, okay? So let's look at penetration of light into the ocean. So here you have depth, and here you have the percentage of surface light. So this is 1, what percentage is the fraction of surface light? This is 1. And you can see that in coastal ocean, the penetration of light is only to about 30 meters. Because the water is very turbid. It's turbid because we have lots of nutrients, we have lots of particulates, we have lots of phytoplankton that absorb the light, and therefore the photic zone is only 30 meters. If you go into temperate ocean, then we can reach all the way to about maybe 80 meters. And if you go to the most clearest tropical seawater, you can have light almost to about 250 meters. I was diving with submersibles, and I can tell you that at a depth of 200 meters, I can still see everything through the window and write in my notebook without putting on lamps. However, when it comes to photosynthesis, then the black line that you see here at about 90 meters, this is the end of the photic zone. This is where rate of photosynthesis is equal to the rate of respiration, and therefore we don't have net accumulation of organic matter. Okay, I'll show you. And so if you go and look at an individual phytoplankton organism, you can see that this organism is making, is increasing its photosynthetic rate as a function of light intensity, and it is almost linear for a good part of the light increase, and then it slows down a little bit, and then we reach a plateau. This is the P max. You can increase the light, but it doesn't increase the photosynthesis. And in some cases, additional light even cause what is called photoinhibition, when the chlorophyll is being decomposed by too strong light, and therefore we lower the rate of photosynthesis. And so each organism is having slightly different curve. As you can see here, we have here 3 different groups of organisms. One of them is increasing very fast and then stabilizes. Another one is increasing much slower and increasing. Another one is decreasing very slowly but saturates at a much higher level. And so each taxon and each in different regions has different response to light. And if you take all of them together, then these are perhaps the green algae, these are the dinoflagellates, and these are the diatoms. And if you put it all together, then this integrates all the 3 groups together. And it gives you relative photosynthesis as a function of light intensity. And you can see that at one point, we have a maximum in the water column, and then it starts to decrease. And again, the response of organisms doesn't depend only on light. It also depends on temperature, as you can see here. So for different light levels and at different temperatures, we have various responses. And the more important thing even than temperature and light is really the nutrient concentration. And in this case, we take nitrate as an example. So you can see that different organisms would have different response to growth rate as a function of nitrate concentrations. Nitrate is one of the most important nutrients. The second one, of course, is phosphate. And we also know that iron is important and many other small elements. We talk about compensation depth, which is the rate, because respiration is considered uniform in the water column. It is marked here by this square. Okay, so this is really the respiration as a function of depth. And then photosynthesis, of course, is higher near the surface and decreasing with depth. And at one point, the rate of photosynthesis equal the rate of respiration, and this is called the compensation depth. But this is only compensation depth where the photosynthesis equal respiration. But if you take the integral of the photosynthesis and you compare it to the integral of the respiration, then the compensation depth will be much deeper, somewhere here, okay? And this is called the critical depth, where cumulative photosynthesis equal to the cumulative respiration. And that is, of course, changing from ocean to ocean, according to latitude, according to the availability of nutrients, etc. Okay, so if we look now at the ocean, we talked about it already, that the ocean is warm near the equator. It's becoming cooler towards the pole. And we have this huge temperature gradient from about 30 in the equator all the way to about 1 or 2 or even less degrees around Antarctica in the south and in the Northern Ocean. And we showed already the thermocline, and we have to understand that the photic zone is really at the top of the thermocline. So you hardly can see it because this is 1,000 meters and we talk about 100 meters. So it's about right here, okay? And again, the thermocline, we talked about it, the seasonal. And while we have this thermocline, the thermocline is separating between the nutrient-poor water in the surface and nutrient-rich water in the deep water. So why do we have, why there are low concentration of nutrients in the surface water? The only reason why we have low concentration of nutrients in the surface water is because the phytoplankton is so efficient in removing the nutrients. Okay? Imagine for a minute that you will stop, you will make darkness in the ocean. It's enough that you will make darkness for a few days, and the nutrient concentrations in the surface water will go up. Maybe it's concentrations that are about half of what you see today. The fact that the nutrients are close to zero in the surface, that is phosphate, nitrate, and silicate, is mainly because the phytoplankton is so efficient in taking up the nutrients, because we have a huge gradient here. So if you stop photosynthesis very quickly, the concentration will become similar between the deep water and the surface water. I hope this is clear. Okay, so the phytoplankton is using both nitrate and phosphate. And if you make a general picture for the whole ocean, then you get very good correlation between phosphate and nitrate all over the oceans, Atlantic, Pacific, and Indian Ocean. And some people say that maybe nitrate is a limiting nutrient because right here we still have some concentration of phosphate before we go to zero, but the nitrogen is already zero. I'm not really sure about it. This is not so important. From experiments that people have done measuring primary production of phytoplankton in the ocean, if you increase only phosphate, it doesn't do anything. If you increase only nitrate, it doesn't do anything. If you increase both of them together, then you get more photosynthesis, okay? So we need both phosphate and nitrate, and now we also know that we need iron and we need zinc and we need other elements, that trace elements that are all needed for photosynthesis in the ocean. But the very well described relationship between nitrogen and phosphorus is a ratio of 1 to 16 between phosphorus and nitrogen. And this led to very famous ratio called the Redfield ratio. Redfield and others were the people who discovered this in the 1940s of the 20th century. And they found that if you want to look at phytoplankton, then they take 106 molecules of carbon, some water, of course, which is not important because we have so much of it, 16 molecules of nitrate, and 1 molecule of phosphorus, okay, of phosphoric acid. And that makes a composite organic matter that looks like this: 106 molecules of carbon, reduced carbon, 16 molecules of reduced nitrogen, and 1 molecule of phosphorus. So this is the Redfield ratio. It is carbon to nitrogen to phosphorus, 106 to 16 to 1. And only in the past 25 years, iron was added to it. If we want to put it in the same ratio, 106 to 16 to 1 to 0.0075 atoms of iron, okay? And this is, for the geochemists, this is the big chemistry of the ocean that is driven by phytoplankton, zooplankton, photosynthesis and respiration. Of course, respiration does the opposite. It takes oxygen and reduces, this oxygen was produced by photosynthesis. You take this oxygen, you oxidize the organic molecule, you get back phosphate, nitrate, water, and of course, CO2. And if we look again at the pictures that I showed you before of the elements that are found in the ocean, so these are the elements that are in high concentrations and are conservative. They don't really change much in the ocean. And the reason for it is because they are not really utilized by organisms. On the other hand, all the organisms that you see here, phosphorus is the example, silicon is another one, of course, nitrogen and others, zinc and others are right here. So these are nutrients. And the nutrients are strongly affected, nitrogen is here. The nutrients are strongly affected by the phytoplankton, and therefore they show big depletion in the surface ocean and big increase in the deep ocean. Other elements have their own chemical behavior, and some of them may be connected to biology, others not necessarily. For example, cadmium is considered to be related to phytoplankton, but this is still being debated. So if you then look again at the gradients of that you find, the vertical gradients that you find in the ocean, you have the temperature gradient, which makes a thermocline. You have a salinity gradient that usually surface water are more saline. Then you have a salinity minimum, and then you have an increase in salinity. I will talk about it later. Then you have total inorganic carbon that shows basically a nutrient gradient that is low in the surface, deep in the deeper water. But if you look at the numbers, they don't go to zero at all. The numbers are much smaller than that. And if you look at other elements like nitrate or compounds, so nitrate really goes to zero. Silicate goes to zero because diatoms takes it from the water column. Barium goes to zero, and phosphate goes to zero. Okay, so all these elements are biologically active, and they are the ones that are affected by organisms. I don't want to talk about the total inorganic carbon and alkalinity because I will have a special lecture just on that. Okay, now opposite of the nutrients, here is nitrate, is the oxygen. Oxygen is very high near the surface, both because it is exchanging with the atmosphere, and the atmosphere has lots of oxygen, but also because the primary producers are producing oxygen. Then, just below, at the base of the thermocline, lots of organic matter get oxidized, and therefore we have oxygen minimum. And in the deep water, surprisingly, the oxygen is increasing. The reason why the oxygen is increasing in deep water is because of the deep circulation. So the North Atlantic deep water and Antarctic bottom water are water that were just not long ago in contact with the atmosphere, and they bring the oxygen to the deep water. They also bring the oxygen to the bentos. If not for the general circulation of the ocean, the bentos would have not have oxygen. Okay, so here we look at the profiles of phosphate and natriate. On the left, you see a phosphate profile, 0 to 4,000 meters. And on the right, you can see profiles of nitrate. And note, the concentrations are very, very low. We talk about micromoles per liter. So at the surface, as I said before, it is all zero. Just sometimes we just cannot measure it. And you can see that in the Atlantic Ocean, the deep concentrations are not so low. They are not so high. They are intermediate. In the Indian and the Pacific Ocean, the concentrations are much higher. They are almost twice as high as in the Atlantic. And we will talk about why that is so. When we talk about nitrate, the picture is very similar. Here is the Atlantic, here is the Pacific and Indian Ocean. They have higher concentrations of nutrients in the deep water. Okay? And this is what we call the biological pump. So here is our phytoplankton doing photosynthesis in the photic zone. Then we have the grazing of the zooplankton. I emphasized it already. They also do a fair amount of respiration and excretion. The fecal pellets and are falling very fast into the deep ocean. Part of them are getting aggregated in what is called the marine snow, which also accumulate fast into the deep ocean. And of course, microbial activity is oxidizing all these particulate organic carbons, and some of the deep zooplanktons are feeding on it, and etc. And then very small part of it reaches all the way to the bottom. Okay, If you want to look at it with another schematic, so here we have the large phytoplankton, small phytoplankton, bacteria. They are all doing photosynthesis in the photic zone. CO2 is getting from the atmosphere, and therefore they make organic carbon. The organic carbon get oxidized, but part of it continues to sink, and part of it continues to sink all the way to the bottom. How much? I would say that maybe if you take the primary production as 100%, then what reaches the bottom is 1%, and what accumulates in the sediments is only 0.1% of what is produced in the surface. Okay, so the recycling efficiency of the microbes, mainly the microbes, is very, very strong. Okay, good. So what you see here is therefore a schematic that shows how the falling particles are falling. Many of them get oxidized in the water column and eventually come back with upwelling water. Downwelling water are coming, as we said, for the circulation, and part of the organic carbon and the nutrients that come with it are buried in the sediments and remain for the fossil record. This schematic is described here by Wally Broker and colleagues. And so what you see here is, first of all, a picture of the deep circulation and surface circulation of the ocean. This is the Atlantic Ocean, this is the Indian Ocean, and this is the Pacific Ocean. The sizes of these squares is similar to the size of the oceans. Right here we have the North Atlantic deep water, which sink down, and right here reach Antarctica. There we have another source of deep water, the Antarctic bottom water, and together they go around Antarctica and continue into the Indian Ocean. Part of it goes in the southern Indian Ocean, part of it goes into the northern Indian Ocean, and then the circles that you see here, these are regions of upwelling where the water come back to the surface. So here you have some upwelling, here you have some upwelling, here you have some upwelling, and here, and then the water continue to the South Pacific, and from the South Pacific to the Intermediate Pacific, and eventually all the way to the North Pacific. So right here, in this spot, you have the oldest seawater that we have in the ocean. They sank here and arrived to this location where they come up to the surface, okay? So how old is this water? We know it. We know that the age of this water, this strip that goes all the way here, all the way to the North Pacific, takes about between 500 and 1,000 years. So this is the circulation time of the ocean, about 1,000 years, okay? And indeed, the water here have very low oxygen. The water here have very high oxygen. Here it's intermediate. And whenever the water come up to the surface, we have return currents that go by surface currents. You see them here with this broken line all the way back to the North Atlantic and to the water around Antarctica. In a vertical profile, you can see the same picture. North Norwegian Sea, water are sinking. Part of them are coming to the surface back, and particulate organic matter is falling down. The same is happening in the Indian Ocean. Only the pathway is longer, and then it also comes back to the surface, and meanwhile, particles are falling. And then we have the Southern Pacific, which is what you have here, with particles falling, and the Northern Pacific. And then all this water come back to the North Atlantic because of the continuity principle. Now, the water that are sinking, not only here and also around Antarctica in the south, they are surface water. They see the atmosphere and therefore they are rich in oxygen. Not only that they are rich in oxygen because they see the atmosphere, but also they are very cold. And the solubility of gases is a function of temperature, and therefore these water are loaded with oxygen, also with CO2, by the way, and then they start to migrate along this very long pathway. The particles that are falling here get slowly oxidized, and therefore the deeper water get enriched with nutrients, but not only with nutrients, also by CO2, according to the red-field ratio that I showed you before. Okay, I'll leave that one. And in this map, you can see areas where we have hypoxic water. What is hypoxic water? It's areas where the concentration of oxygen goes down, 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 almost to be anoxic. Okay, hypoxic is half anoxic, and when you have this concentration, it's already almost anoxic completely. That is, we have bottoms that are without oxygen. And so what you see here is that we have several regions in the ocean right here off the coast of North America and off the coast of South America, off the coast of Africa, off the coast of Arabia, and in parts of the Indian Ocean, surface Indian Ocean. We have very, very low oxygen values. The reason why we have very low oxygen values here is because we have upwelling here. And the upwelling is bringing nutrients to the surface, and the nutrients are taken by the phytoplankton, and it sinks to the bottom and makes almost anoxic conditions because of the microbial activity. So if you look here, these are the upwelling regions of the ocean, and it is very similar to the, it is very similar to the picture that I showed you before of the anoxic regions, okay? And let's look at the upwelling regions where there's deep water come to the surface. So first of all, off Namibia, this is Walvis Bay, an area where you have lots of mammals, and then we have off Spanish Sahara. Again, all these areas are big fishing areas where you have lots of fish, off Portugal, off California, of South America, Peru current, Chile current, and then near India and in Arabia, you have Somali, you have areas of upwelling, and these areas of upwelling is where you have nutrients, you have zooplankton, you have phytoplankton, that and eventually lots of fish. So it's good fishing grounds. Here is what is happening. The currents in this case, or it's driven by the wind, and it takes the currents along shore. And if this is in the Southern Ocean, then Coriolis force takes it to the left. And when you bring water away from the continent, water have to come from below to the surface, and this is how you get the upwelling. And when you have upwelling, then you have lots of phytoplankton, zooplankton, and fish. So upwelling is very important for fisheries, and this is the areas where most of the fish are being collected around the world. At the same time, because of the high primary productivity, you have a big oxygen minimum zone where at around 1,000 meters at the base of the thermocline, where you don't have enough oxygen. It's all consumed by the microbes and the zooplankton. And the reason why you have a high oxygen below is only because of the deep circulation of the ocean, because of the advection of the water from the north and from the south, okay? So here is, for example, an oxygen profile in the Atlantic. As you can see here, the concentrations are given here in a micromolar. So here is the North Atlantic deep water, has very high oxygen concentration because it comes from the surface, from the north. You can see the core of the North Atlantic deep water, and it is still maintaining 240 micromolar of oxygen and get depleted and depleted. But right here, it gets another boost of oxygen from the Antarctic bottom water, which brings it all the way to here. Below the thermocline in the equatorial regions, we have strong oxygen minima as you can see it here. And in between, we have the Antarctic intermediate water, which is what you have here. Okay, so this is what I mentioned before, that if we have a amount of primary productivity at a certain depth, 100 meters in the water column, once we reach 1,000 meters, only 1% of it is still organic carbon that can be oxidized. And when we reach the deep water, it is 0.1% that is being buried for the future. And again, when I say for the future, it's only for 1,000 years. If we go longer, then it continues to be oxidized within the sediments. So the oxidation doesn't stop. The microbes are still active. Okay, so now we think about it in view of the increase in atmospheric CO2. And we also see, and I will talk about it in more detail, we see also increase in CO2 in the surface ocean, because it increases in the atmosphere, and therefore it increases also in the surface seawater. Okay, we talked about it, and right here, we look at the surface distribution of nitrate, and you can see that most of the ocean is blue. Blue ocean means concentrations that are extremely low, less than 1 micromolar most of the times. And as I said, this is happening only because the phytoplankton is so efficient in removing this nitrate. As you go to around Antarctica, you have two phenomena. First of all, the water becomes very cold, and the phytoplankton is lower. Secondly, you have much less light, and therefore much less productivity from that point of view. And then the third thing is really that the water is sinking, and therefore good part of the organic production is carried down to the deep water with the sinking water. And so that is the reason why, in addition, around Antarctica, because of there is a very strong current that goes around Antarctica in this direction. It takes in the Southern Ocean, Coriolis force is taking the water towards the north, and therefore you have upwelling around Antarctica. It makes lots of productivity, but most of that productivity is sinking. But still, this is the area where you have lots of whales and, of course, krill and lots of life, even though the temperature is so cold. Okay, and here you can see surface water productivity estimates. This is not simple measurement to make, and so right here you can see again the upwelling areas, Walvis Bay, Spanish Sahara, Peru and Chile, California current, around Arabia, etc. And this is the high primary productivity that is around Antarctica. And also in the Northern Sea, we have a relatively high productivity. This is actually the same, so we can skip it. And at the end, this is what produces the sediments of the ocean. And this is a bit complicated map, so let me go around it and explain. So this is the distribution of sediments on the ocean floor. What you see here is in this blue color, this is calcium carbonate, both in the Atlantic Ocean and also in the Pacific Ocean and in the Indian Ocean, right here, okay? Lots of calcium carbonate, about 50% of the ocean floor is covered by calcium carbonate. And we will talk about it a lot. Then you have the deep parts, which are here. These are called the abyssal plains in the Pacific, and the same abyssal plains in the Atlantic, and then the abyssal plains in the Pacific. The abyssal plains in the Pacific are run away. In the Pacific are all residual sediments after all the calcium carbonate has dissolved. And what we find in the sediments is either siliceous sediments and what is called red clay, or we find siliceous sediments, which are from the productivity of diatoms. So all this region is full of diatom shells, right here in the equator. This is diatomite sediments that indicate very strong productivity. And the calcium carbonate, of course, is dissolving because of depth, but we will talk about it next. Okay, so this is the end of this lecture. And I think we will not take a break. I will open the next presentation. Okay?
Yes, okay.
Yeah, I do stop share for a second. And I will I will open that presentation as well. Wait a second. You see it?
No.
So I need to share again.
Yes.
Wait a second. On the Teams. Okay.
Okay.
Now you can see it. Let me go to presentation mode.
Hmm?
Okay.
Yes, perfect.
Good. Okay, so I will also cover now the questions that were asked before, what we think about the lowering of the circulation and also about the connection between CO2 and warming. Okay, so this is well known, the killing curve. We talked about it before. You have to remember this curve. This is the most important. The measurements really started in the late 1950s until they really made it well. And it continues until today. The concentration today, as you can see, is already, this is 420. It's already 425 or so. So it continues to increase in a very steady. You can also see the rate. The rate was relatively low during the 1970s and 80s, and then it increased, and now it is even increasing and continue to increase together with the increase of number of humans on Earth and the consumption of fuel. And just to show you how important is this thing, is you can look here in the record of the last 2,000 years, and you can, 1,000 years, start here at 0, and then you have the last increase associated with the Industrial Revolution right here, and then the present day increase, which is so strong. We reached our concentrations that are above 420 parts per million, while in the last 1,000 years, it was all similar and was around 280. And I already mentioned that this 200, we are now at 420 around here, but I showed you already that this increase is very, very dramatic compared to the natural fluctuations of CO2 that were between the glacials and the interglacials. And here it goes down only to 400,000 years, but it continues for about 2 million years back. We have very good record of the CO2 concentration in the atmosphere. And therefore, people asked, since we had such strong fluctuations, why do we have global warming today? we have such global warming today because CO2 is a greenhouse gas and because it increased to concentrations that we did not have for several million years back. And as you remember, as you see, this was the limit, 220, 280, perhaps 300 ppm, not more than that. And now we are doing something which is extremely dramatic. We are now at about 420, and the prediction for 2100 is that we will have above 560 or 600 ppm, which is what we call CO2 doubling, okay? So I don't care much about predictions, but it is certainly clear that we already have concentrations that are twice as much as we had before, and this is absolutely a tremendous increase in the greenhouse gas CO2 concentration, which is starting a cascade of reactions that increase the temperature of the ocean and the continents. And the instrumental record of temperature, I showed it to you before. I don't think I have it here. Yeah, I do have it here. So sorry, I will show you. I show it next. You see it? Hello? Hello?
Okay, sì.
Yes.
Yeah, you see it. Okay. So here is this is now the temperature record. So how do we know the temperature? The instrumental record is only here. You know, the last 100 years or so, we had instrumental records. But all these records that you see here is records that we have from several paleo archives. The most important, perhaps, are corals. Corals have annual bands, and the annual bands of corals can go back up to about 600 years, so around here. And in the coral skeleton, we can measure oxygen isotopes, and we can measure strontium to calcium ratio. Both of them are proxies for the ocean temperature, surface temperature water. And we know that this is roughly the temperature. So it was, the temperature was more or less uniform and much lower than what we have today, because we have here the increase, and these are predictions, so I don't care much about predictions, but this is 2000, we are today at 2025, so we are here. And we are right where the predictions told us that we are going to be. So we have, and if you take the average and the deviations, so the deviations today are already around 1 degree or 1.5 degree above what we used to have. And this is not the only temperature record. We also have temperature record from the ice cores. We have temperature records from tree rings, and we have temperature records and from caves and stalagmites, etc., on land. And so altogether, if you put it all together, it's quite clear that we have global warming of about 1.5 degrees almost, and that the predictions are certainly for 3 or 4 or 5 more degrees if we don't stop increasing the CO2 concentrations. Now, I must say that the CO2 itself is not causing all the warming. It is only the trigger that starts. It's probably responsible for 20 or 25% of the increase, and the rest is from feedback mechanisms, like, for example, ice melting. When you have ice melting, you have less ice reflection and therefore more absorption of the sun radiation. So this is a very strong feedback mechanism. And there are more that I don't want to expand on. But at the moment, it is quite, I would say 99.9% of the scientists would agree that the global warming is because of CO2 increase. Okay, so let's now talk about some processes of the global carbon cycle, and we will talk about it very quickly. So we saw this already. I don't want to repeat it. And here I want to expand a little bit on this figure that we saw before, but now I want really to explain what it means, okay? So let's look at it. The atmosphere, this is like from 5 years ago or something like that, okay? Um, the reservoirs of fossil fuels is 4,000 gigatons of carbon, okay? More than 4,000 gigatons of carbon. It keep increasing because the oil companies and the gas companies keep on finding more and more fossil fuels, okay? Um, in the atmosphere, we have only 840 gigatons. The units that we are talking about is gigatons carbon, which is petagrams of carbon, or 10 to the 9th tons of carbon, which is gigaton, okay? And 840 is not so much. This is what we have in the upper ocean. In the upper ocean, you see here, we have 800 gigatons of carbon in the surface ocean. And in the deep ocean, on the other hand, I'm sorry for that, but in the deep ocean, we have 3,800, okay? Almost 40,000 in the entire ocean. And if you add to it the calcium carbonate sediments, then it's another 4,000 to 20,000 additional gigatons of carbon. So altogether, the ocean dominates the carbon cycle of our planet for the short time scale, for the circulation time of the ocean. And what happens in the ocean really will determine what is happening in the atmosphere. So we send every year 10, this year it's already 12 gigatons of carbons into the atmosphere. But what accumulates is only half of it. As you can see, the increase is only 5 gigatons of carbon per year. So where are the other 5 gigatons? Well, if you look at the exchanges between the atmosphere and the two other ecosystems, the ocean and the continent, then you can see that the continent is actually a very small reservoir of carbon. It is 560 gigatons. All the land plants together, all the Amazon and tropical forests and high latitude forests are only 560 gigatons, less than what we have in the atmosphere. The biggest reservoir on land is really the soils. Soils contain a lot of carbon, like as you can see, 1,500 out of 2,000, okay? So 2/3 of the carbon on land is really in soils. Now, that ecosystem has very strong fluxes to the atmosphere and back. But as you can see in my schematic here, I put here that 120 gigatons go back to the atmosphere, and 60 and 62 together go into the land ecosystem. So we have that as an unbalance. Instead of 120, it's 122. So 2 are taken into the land ecosystem. And into the ocean, we have similar budget. 90 goes back to the atmosphere, 93 goes into the ocean, and the difference is 3. So 3 and 2 together, it's 5. What accumulates is 5, and 5 get absorbed by the oceanic ecosystem and the continental ecosystem. Okay, so this is the way we understand the carbon cycle today. Okay. How do we know all that? And how certain we are about these numbers? Okay, so some of these numbers are really clear and measured and well known. Others are more speculative, as I will show later. Right here, before we leave this picture, I would like to mention that people say, oh, we have so many human beings. Okay, so 8 billion human beings on Earth, their biomass is only 0.06 gigatons carbon. It's minuscule. We are 0. Okay, we are not important in the whole game. We are only the ones that send these 10 gigatons per year to the atmosphere. Okay, so Each one of you, if you make the calculation, I'm talking about Europe people, each one of us is emitting to the atmosphere about 2 tons of carbon per year. Just imagine that you are carrying on your back, each one of you, 2 tons of carbon that you send to the atmosphere every year. It's a huge number. Now, in the ocean, of course, on land, we have lots of processes. We are not going to talk about them. But in the ocean, we have, first of all, chemical equilibration. You increase the CO2 in the gas phase, it increases in the water phase. So this is making chemical equilibration. CO2, unlike other gases, is a reactive gas, and therefore it makes lots of carbonate chemistry that I will talk about next. But in addition, we have 2 biological processes. The first one we already talked about, photosynthesis, takes CO2 and water, makes organic matter and oxygen, sends part of this into the deep ocean. The second process, which is, and Damir talked about it, it's calcium carbonate precipitation. Lots of people talked about biomineralization. I have to mention that all the calcium carbonate precipitation in the ocean today, 99.9% of it is all biological. There is almost none calcium carbonate precipitation chemically in the ocean. It is all biological. This calcium carbonate falls down to the ocean floor. In the deep water, we have 2 opposite processes. Instead of photosynthesis, we have oxidation of organic matter, and the calcium carbonate part of it, about good part of it, maybe 80 or 75%, dissolve back and make calcium and bicarbonate. Because we have deep circulation, this CO2 and this calcium carbonate come back to the surface water. And this is caused by the deep circulation of the ocean that we talked about. Okay? So here is the increase in atmospheric CO2 in different latitudes. You can see that the seasonal cycle is changing. For example, in the southern hemisphere, there is almost no fluctuations. In the northern hemisphere, we have very strong fluctuations. This is because the land mass in the northern hemisphere is much bigger than the land mass in the southern hemisphere. Okay, but the most important thing on this figure is really this line, which is the amount of CO2 that we emit to the atmosphere. And right here, all this is the missing CO2. That is the CO2 that is not found in the atmosphere, even though we sent it to the atmosphere. So where did it disappear? Where is all this missing CO2? Okay, well, if you want to look at this picture in that way, then you can look at it like this. So this is 1850, 1990, and these are the budgets of the calcium carbonate. So addition to the atmosphere is here, removal from the atmosphere is here, and here we try to understand the total budget. So let's look at what we know. First of all, emissions from fossil fuel in blue. This is the record that we have here. This is very well known because it is measured by the companies that burn the fuel, and therefore we know about it very well. The second thing is really the increase or decrease of the land ecosystem. So you can see that there is a little increase, perhaps, of the land ecosystem, and there is a big arguments about this, if this is correct or not. Whatever you have to take off this, you will have to put somewhere else, okay? So this is, as I said, roughly estimated. The next one is really an unidentified sink that we don't know where it is. It's only calculated, and I will tell you in a minute how we calculate it, okay? The next sink that we have is the oceanic uptake. It's here, that one. And the only oceanic uptake is relatively well known because we are measuring the total CO2 increase in the ocean in many stations that people take along the ocean. And therefore, we know it relatively well today. In the past, it was less detailed, of course, but today we know it very well. And the next one is also very well known, and that is what accumulates in the atmosphere. So this is this one, okay? So this is well known from the killing curves that we talked about before. So we know how much we release. We know how much is accumulating, which is what you see here. We have to account for what is missing, and what is missing has to be somewhere. So either in the land ecosystem or in the oceans. And most probably it is in the oceans, what you see here, in the oceans, and therefore, sorry, in the oceans, it must be here, and perhaps here, and we still don't know how to close properly the budget. Okay, good. The ocean is taking CO2, we know it, because, for example, you can see the concentration of total CO2 in the ocean, and you see that it is increasing from 1984, where they started measuring, to 2012. The CO2 is increasing. The PCO2 is increasing. The pH is decreasing, okay? And so we have record from the ocean. We know that the ocean is increasing, okay, as you can see here. So let's talk about the chemistry. How does it happen? So CO2 gas exchanges with the ocean, and we have CO2 becoming dissolved CO2. The dissolved CO2 reacts with water and makes carbonic acid. The carbonic acid releases proton and makes bicarbonate. So this is carbonic acid, this is bicarbonate, and this is one proton. And the one proton releases another, the bicarbonate releases another proton, as you see here, and we get the carbonate ion. So this is dissolved CO2, carbonic acid, bicarbonate, and carbonate. All of them together are called the total CO2, okay? Now, each one of these reactions is controlled by a constant. This is Henry's constant, solubility, then the K0, K1, and K2. And these are all equations that we can write because we know the constant. And so we have four equations, 1, 2, 3, 4 equations, and we have concentrations. So here is CO2 concentration, here is dissolved gas concentration, here is the carbonic acid concentration, here is the bicarbonate concentration, here is the proton concentration, and the carbonate ion concentration. So we have, if you mark them, 1, 2, 3, 4, 5, 6, we have 6 unknowns and only 4 equations. In order to solve the carbonate system, we have to measure 2 additional parameters. And it seems simple that we first of all measure the pH, which is the hydrogen ion concentration. And the other one that we measure, it turns out to be the total CO2, which is the sum of all the species of CO2 that we see here on this equation. Okay, so as I said, each one of them is an equation. Here is one equation, and here is a second equation, and a third equation. This is the fourth equation. I don't want to discuss it. We know the values of K1 and K2. Here we combine the CO2 aqueous with the carbonic acid together because the carbonic acid is only 1/700 of the CO2 aqueous. So we call it CO2 star, and we combine them together, as you see here. So this is the equations. We have 3 equations, and we have only 5 unknowns in this case. And so we can solve the system. K1 is roughly 10 to the minus 6. K2 is 10 to the minus 9. Easy to remember, okay? And so if we define now another variable called DIC, or total CO2, dissolved inorganic carbon, total CO2, CT or CI, lots of names, but it is all the same. What it is, CT means CO2 aqueous, including the CO2, the carbonic acid, bicarbonate and carbonate together. So if we take all of them together, we have another parameter in addition to the pH that we can use for our equations. Okay, now it is relatively easy to measure the total CO2. What we do is we take a bunch of seawater, we add strong acid, all the carbon, the carbonate ion becomes bicarbonate. When you take protons, the bicarbonate takes another proton, becomes carbonic acid, the carbonic annex becomes CO2, and we take this CO2 out of the water and we measure it by simple manometer, that is a pressure gauge, and we can get the total CO2. So if we know the total CO2, then we can write the following equations from the algebra that you had before, and I can show it again, but we will not go through it. The CO2 is equal alpha 0 times total CO2. The bicarbonate equals alpha 1 times total CO2, and the carbonate ion equals alpha 2 times total CO2. And the values of the alphas are the following. You see that they are only function of the pH, which is hydrogen ion concentration, and the constants, K1 and K2. So the denominator in all these equations is the same, H square, K1H, K1 times K12, and for the CO2, for alpha 0, this is H square on the top. For bicarbonate, it's H times K1, and for the carbonate ion, it's K1 times K2. And you can see these ones are actually the three components of the denominator. So in each one of them, if you multiply it by CT, then you get the concentration of CO2, of bicarbonate and carbonate. And this is how we are doing it. So we are measuring pH, we are measuring the total CO2, and we calculate the concentrations of the three different species. Okay, I don't want to go into calculations, but you can easily see that this is relatively easy calculation to make even by head. For example, for pH 8, the hydrogen ion concentration is 10 to the minus 8, okay? And therefore, H squared is 10 to the minus 16. H times K1, H times K1 is 10 to the minus 14. K1 times K2 is 10 to the minus 15, okay? So if we try to calculate, for example, for pH 8, we can calculate that the bicarbonate is 100 times higher than the CO2 and 10 times higher than the carbonate ion, okay? Because that one is 10 to the minus 16, that one is 10 to the minus 14, and that one is 10 to the minus 15, okay? And so you can easily make these calculations. If you know logs, you can do everything with logarithmics. It's even easier. I don't think I have it here. So instead of pH, we talk about instead of H concentration, we talk about pH. Instead of K1 concentration, we talk about pK. And therefore, the log of the ratio between bicarbonate and CO2 is just pH minus pK1. Okay, and when pH equals to pK1, then the concentration of bicarbonate equal to the concentration of CO2. And the same is true for pK2. So if we look at the final calculation, so here we have percent of the total CO2. This is TIC, or as we said, CT. And here you have the pH, and here you have pK1, which is 6. And at pK1, the concentration of bicarbonate is equal to the concentration of CO2. As you can see, concentration of CO2 goes down very strongly, and at pH of seawater, which is about 8, it is very, very small. The bicarbonate is the dominant one. You see, in all the pHs that we talk about, it is the dominant species. And then the carbonate ion concentration is here, And in the pH of seawater, it is around here, 8 or so. It is higher than the CO2, but also relatively small. So here is seawater, and you can see this is the bicarbonate concentration, this is the carbonate ion concentration, as this is the CO2 concentration. Now imagine that this is really quite amazing, because the bicarbonate is the dominant species and nobody takes it. Nobody needs bicarbonate. The algae want CO2, and CO2 is very low. The calcium carbonate precipitation wants the carbonate ion. It is not so low, but it is still rather low, okay? And the bicarbonate is used for nothing, okay? It is only a big reservoir that if you take from it CO2 and you take from it carbonate, then it compensates for it, okay? And how does it happen? To do that, we need to define another variable. That variable is called alkalinity. Now, I don't know how many of you ever heard the term alkalinity. It is not what you think. It's not the opposite of acidity. Okay, alkalinity in oceanography is defined in a very funny way. It is the sum of the sodium and potassium and calcium. It is charge balance, okay, between the cations of the strong bases and the anions of the strong acids. So, okay, if you take sodium and potassium and twice calcium because it has a charge of 2, and twice magnesium because it has a charge of 2, and hydrogen, all these together are the strong cations, so to speak, minus chlorine, which is a strong acid, and minus 2 times sulfate, which is again a strong acid. So we take all the cations of the strong bases minus all the strong anions of the strong acids, and then it minus bicarbonate, twice carbonate, minus OH, minus borate, and all that equals to 0 because the charge balance has to be kept. So this part of the equation that we see here, we call this the alkalinity of seawater. I know that this sounds like a very strange definition, but believe me that this is how it should be defined. So again, sodium and potassium and twice calcium and twice magnesium minus chloride minus sulfate equal to bicarbonate, 2 times carbonate, borate, and OH minus H plus that we moved from this side to this side. And this is called the alkalinity, the total alkalinity of the ocean. You will see in a minute why we use it, because it is very useful parameter, okay? Good. So if we want to see what is really alkalinity, so here is the concentration of the cations and anions in seawater. We have lots of sodium, we have lots of magnesium, we have a little bit calcium, and a little bit potassium, and that is all, okay? These are the cations that we have in the ocean, the important ones. Then if we go with the anions, we have chlorine, which is very high, twice sulfate, which brings you all the way, and the little thing that is left here to make it equal to the other side is really the bicarbonate, twice carbonate, and the borate. Okay, that's all. So this is the entire total alkalinity that we talk about. But that total alkalinity is extremely important. It is extremely important. I can leave that one away. It is extremely important because it tells us a lot about processes that are happening in the ocean. And it also is an easy parameter to measure in addition to the DIC, okay? So what is behind the concept of alkalinity? So imagine that when the ocean was formed, it was all distilled water. And then whoever created the ocean decided to add sodium hydroxide, okay? So it put 1 millimolar of sodium hydroxide into the distilled water, and now the alkalinity was very high. It was 1 milli equivalent per liter, and the pH was very high. It was around 12 or 13, something like that. So, wow, pH so high, the organisms cannot live in the ocean. So whoever made the ocean decided to add some acid to it. So he took HCl and added HCl again, 1 millimolar, and surprise, the pH came back to 7 again, as it was before, but now we have sodium and chlorine in the ocean, and the pH remains 7, okay? So if you titrate all the strong bases by all the strong acids, you get a lot of salt, but the pH remains 7, okay? So this is what was happening. And then somebody made a mistake, and instead of adding sodium and HCl, sodium hydroxide and HCl, and calcium hydroxide and sulfuric acid and magnesium and sulfuric acid, etc., he added to the seawater a little bit calcium carbonate. Wow, calcium carbonate doesn't dissolve much, and it makes weak acid, which is the carbonic acid, and the bicarbonate and the carbonate ion. This is finally the total alkalinity. So now you understand what is really behind the total alkalinity, because if all what we did, we would add sodium chloride and magnesium sulfate and calcium chloride to the ocean, we do not have alkalinity. They all balance each other. But if we add dissolved calcium carbonate or sodium bicarbonate or potassium bicarbonate, then we start to accumulate alkalinity, which is the sum of the weak acids in the seawater. So, sorry, you can see it here again. So this is the sum of the weak acids. Look, the bicarbonate, the carbonate, the borate, the OH, these are the weak acids in seawater. And the weak acids in seawater are the buffer of the ocean. And this is why alkalinity is so important, okay? So the alkalinity is highly useful because when you precipitate calcium carbonate, you take calcium and 2 bicarbonates, and that makes calcium carbonate and water and CO2. And therefore, this part is a part of the alkalinity is decreasing. We decrease the calcium, so we decrease the alkalinity. And therefore, if we measure the alkalinity when calcium carbonate precipitates, we measure the alkalinity at the beginning of the process and the end of the process, we can tell how much calcium carbonate precipitated. If we dissolve calcium carbonate, we do the same thing, but the opposite. We increase the alkalinity, okay? And therefore, because the alkalinity equals to this, and we can also calculate very easily the pH, and if we plot alkalinity versus DIC, total CO2, we can put equal pH lines, okay? Because it is all determined by the pH and the constant, as I showed you in the equations before. And therefore, if we start with pH of 8.3, and now all what we do, we add inorganic carbon, DIC, we add to seawater inorganic carbon, we go in this direction, and what is this? This is ocean acidification. This is what is happening today in the ocean. We increase the total CO2, and therefore we lower the pH, okay? And when we make a plot of total alkalinity versus DIC, and I showed you before, but this time it's with real numbers that you can calculate. So the DIC in the ocean is from 1.9 to 2.15, the alkalinity from 1.9 to about 2.45. And here are the processes that we can learn from such a diagram, where the blue lines are pH, equal pH lines, okay? This one. Here it is 7.8, here it is 8, here it is 8.2, the pH. And then equal CO2 lines are here, 8, 11, 15, 20, and 30 micromolar, okay? And now let's look at the processes. So the first one I showed you already is when CO2 invades the ocean, you increase the CO2, the total CO2, but you don't change the alkalinity because you only add CO2. and therefore the pH is decreasing, and the total CO2 is increasing. If you do the opposite, you take seawater and you bubble nitrogen in it, then you remove CO2 and the pH will go up. Okay? The second process is really photosynthesis and respiration. It is almost the same as CO2 invasion or removal, with a slight difference, and that difference is caused by the nitrate. I don't want to expand on it, but therefore it is not exactly horizontal. It is slightly tilted according to the Redfield ratio, if you remember it, 1 to 16. And therefore, sorry, it is 106 to 16, which is a ratio of 7. And therefore, this is the tilt. And so this is photosynthesis. You remove CO2 and you remove nitrate, and you increase the alkalinity a little bit, and you decrease the DIC strongly. If you make respiration, you increase the CO2 and you decrease the alkalinity a little bit, and therefore it goes along this line. The most important one is this vector that you see here at a slope of 2 to 1, and that is the alkalinity change. So if you precipitate calcium carbonate, then you lower the alkalinity by 2 units because calcium has a charge of 2, and you lower the DIC only by 1 unit, and therefore you get a vector which looks like this. And if you dissolve calcium carbonate from the origin, you go in the opposite direction. Therefore, if you have this plot, which is called the DFAS diagram, if you have this plot, you can learn all the processes that happens in seawater, and you can easily graphically say what is happening in your seawater if you know how to use this diagram. Okay, so I'll skip that one. Coming back to the bell-shaped diagram, in this case, it's a logarithmic. So this is a bicarbonate. As I said, it's not really being used much. Here is the carbonate ion that, of course, goes down when you precipitate calcium carbonate. And here is the CO2, which goes down when you make photosynthesis. And when you make ocean acidification and you add total CO2 to the system, it lowers the pH, and therefore it increases a little bit the bicarbonate, but it decreases the carbonate ion, as you can see this arrow, and it increases the CO2, as you can see in this direction. Okay, so this is, now I want to say one more thing that I showed also in the previous slide, but here I want to emphasize it. When we precipitate calcium carbonate, we take out calcium from the seawater and we take bicarbonate, and therefore the alkalinity is decreasing, and we precipitate calcium carbonate. But at the same time, we produce CO2 and H+. And why are we producing CO2? Because this process is decreasing the pH. If you remember the previous slide, sorry, this one, when you precipitate calcium carbonate, as you see here, we lower the alkalinity by 2 units, we lower the DIC by 1 unit, and therefore we go to lower pH. If we have lower pH, we have higher CO2, as you can see here. We go from maybe 50, from this value to this value in the direction of increasing the CO2 aqueous, and therefore CO2 is produced in the water and it is released to the atmosphere. If it is released to the atmosphere, then, sorry, if it is released to the atmosphere, then when you precipitate calcium carbonate, you take out 1 carbon to the ocean floor, but at the same time, you add 1 carbon to the atmosphere because you do it from surface water. And therefore, unlike what many people make mistake, when you precipitate calcium carbonate, you release CO2 to the atmosphere. Remember that. It is not helping the situation to precipitate calcium carbonate. What you actually want to do is the opposite. You want to dissolve calcium carbonate instead of precipitating calcium carbonate. I hope this is clear. Okay, so Here is the pH of the pH. Here is some construction of what the pH was in the past, about 8.2. And then here is the year 2000. And here is a prediction of what will happen to the ocean pH at the year 2100. It can easily be calculated. And you can see that the carbonate ion concentration is decreasing. You can see that the CO2 concentration is increasing. And as a result of it, we will get more calcium carbonate dissolution. And maybe the organisms that are trying to precipitate calcium carbonate will find it a little bit more difficult to precipitate calcium carbonate because the ocean is more acidic and you have lower carbonate ion concentration. And as I said before, CO2 is being released to the atmosphere when you precipitate calcium carbonate. Okay. So finally, we come to the organisms that precipitate calcium carbonate in the ocean. I know you already talked about it, so I will do it very briefly. Here is coral reefs, and here are planktonic foraminifera. This is the live one. And here are coccolithophores, and these are sea urchins. If you look at this diagram, you can see that foraminifera are probably producing half of the calcium carbonate in the ocean. Corals about 1/8. Echinoderms are very important, about 1/8, and quarter by coccolithophores. Mollusks are very minor in this game, okay? Here is a live planktonic foraminifera. This is how it looks. It's only 1 millimeter in diameter here, but with all the spines, it is much bigger, maybe 1 centimeter, the same here. And it has lots of symbiotic algae, which are the little dots that you see here and here, okay? And planktonic foraminifera produce a lot of calcium carbonate shells that are all sinking to the ocean floor, okay? This is how the sediment on the ocean floor looks. When you look at it, it is all foraminiferal sands, okay? The coccoliths make the fine fraction, which is, you see, this is only 10 micron. So everything that is above 63 microns is foraminifera, and everything that is below 63 microns is usually coccolithophores and clays, okay? We talked about the zooplankton that brings the coccoliths to the ocean floor, and we talked about the circulation and all that. Good, so this we talked already about. And here we come to the next feature that we can find on the ocean floor. The high topographies, which is the ocean ridges and other high spots in the ocean, are sitting above a level which is called the CCD. The spelling of the CCD is a calcite compensation depth, okay? Calcite compensation depth means that below this level, there is no accumulation of calcium carbonate. It's very similar to the marine snow lines, or to the snow line on high topographies on land. So the high topographies are covered with calcium carbonate, and the low topographies don't have calcium carbonate. What is the reason for it? The reason for it is, here is, for example, actual data. So you can see here the carbonate percent in above 3,000 meters, for example, is all 100% calcium carbonate, almost. And then comes a zone called the lysocline, where the percentage of calcium carbonate goes dramatically, very quickly, to very low percentages, okay? If this is 100%, here we talk about almost 0, okay? And it starts to go down around here, okay? And this is the depth of 1,000, 2,000, 3,000, 4,000 meters. We start to lose the calcium carbonate, sorry, okay? These are actually profiles in the Atlantic and the Pacific, so I don't want to show the actual data, but at the end, what you see is that we have lots of planktonic calcium carbonate producers. It all falls down to the ocean floor, and the calcium carbonate accumulates on the top of the ridges of the ocean, the deep sea ridges of the ocean ridges. And then as the ocean ridges cool down, they start to sink. And when they sink below a certain level, this is the CCD that I mentioned, the calcite compensation depth, all the calcium carbonate that is now precipitating on it, because it continues to precipitate, is dissolving. And therefore, the sediment itself does not contain any more calcium carbonate. The only calcium carbonate we have here is what accumulated before when it was on high topography, okay? And therefore, if you look at the map, that shows you that the deep parts of the ocean floor, which are below 5 kilometers in the Indian Ocean, 5.5 kilometers in the Atlantic, and 5 kilometers in the Pacific, are all without calcium carbonate. Only above 5 kilometers, above 4.5 kilometers, you have calcium carbonate, okay? What is the reason for it? The reason for it is very simple. Both in the Atlantic and the Pacific, as I told you, the total carbon behaves like a nutrient, like the nutrients that I showed you before. And therefore, in the Atlantic, we are sitting here, low concentration in the surface water, high concentration in the deep water. The same is true for the Pacific Ocean, except that the total CO2 here is double than the total CO2 that you see here, because in the Pacific, the deep water spent more time, as I showed you before, than in the Atlantic. The Atlantic is relatively fresh water, the Pacific is old water, and therefore it accumulates CO2. So if it accumulates CO2, then the pH goes down. pH goes down, the carbonate ion goes down, and therefore the total CO2 is causing this change in pH. So here is the Pacific, and here is the Atlantic, and this is the opposite picture of the total CO2. And when you lower the pH, you lower the carbonate ion concentration. When you lower the carbonate ion concentration, calcium carbonates start to dissolve, okay? And therefore, if you look now at a parameter called omega, which is the concentration of calcium times the concentration of carbonate divided by KSP, which is the solubility product, you can see that in surface water, both Atlantic and Pacific, we have high omega values here and here. And then at a certain, this is omega equal 1 when we are exactly at equilibrium. And then if we go to concentration, to omega values that are below 1, both for calcite and aragonite, we get at a depth where we get undersaturated, okay? Here it is for the Pacific, here it is for the Atlantic, for calcite, here it is in the Pacific and in the Atlantic for aragonite. And as we go undersaturated, these minerals start to dissolve, and the rate of dissolution, see, that's the same curve. And here is the definition of omega. It's the concentration of calcium times the concentration of carbonate divided by KSP, which is the solubility product. And therefore, they start to dissolve. And the rate of dissolution, I'll skip that one for a second. The rate of dissolution is not linear. The rate of dissolution is exponential. That was found first by a fellow called Peterson in 1996. He suspended calcium carbonate in the ocean and saw that here nothing is happening until the depths of about 3,500. That was in the Pacific. And then suddenly the calcium carbonate started to dissolve very, very fast, okay? As you can see here. The kinetics are not linear. The kinetics are very non-linear. And if you plot it like that, so here is dissolution rate versus 1 minus omega. You can see that at the beginning, when you are close to saturation, the dissolution is very small, and then it quickly increases at tremendous rate that if you want to know how to plot it, so you plot it dissolution rate versus 1 minus omega on a log-log plate. You see, this is a logarithmic scale, and this is logarithmic scale, and then it falls on a straight line. So the equation that describes the rate of dissolution is rate of dissolution equals K times the surface area times 1 minus omega to the power of n. And the power of n was extremely high, 4.5 or so. And this is still not well explained. People think now that actually there are two processes here. One is slow dissolution, the other one is fast dissolution. I don't want to go into it, but the fact is that because of this very strong sensitivity of the rate of dissolution with omega, we have the CCD. We have this very strong boundary that separates between calcium carbonate rich sediments and calcium carbonate poor sediments. And this is, again, lab experiment, field experiments that show how it all dissolves. The area where the dissolution starts is called the lysocline, and then below the lysocline, the percent of calcium carbonate goes very quickly down until it is almost zero. So this is the percent of calcium carbonate. Good. And this is again producing for us what I showed you already before, the map of the ocean floor with lots of calcium carbonate in the Atlantic because it has high topography of the ocean ridges. Then on the ocean ridges of the Indian Ocean, we also have calcium carbonate. In the South Pacific, we also have calcium carbonate, but in the North Pacific, there is almost no calcium carbonate. And even in the South Pacific, if we are away from the ridges, then we have dissolution. And the same is true for the abyssal plains in the Atlantic and for wide regions in the Indian Ocean. And when calcium carbonate dissolves, what remains is clays and silica. So here you have this beautiful siliceous belt around Antarctica, which is caused mainly by the high productivity of the around Antarctica. And here you have the high productivity along the western coast caused by upwelling and into the equatorial upwelling. Okay, so this is what I think. I think I'll stop here, and then we have one more lecture that we'll take about a 5 minutes break now before we finish. Okay, we have time until another 50 minutes, right?
You mean the break or the time?
No. I mean, for lecture, we have another 50 minutes until
7:30 in Israel.
until 7:30. Yeah, so let's take now a break of 10 minutes.
Okay, thanks.
That was a long lecture. Yeah. Okay.
Yes, thanks. Jonathan,
Yes.
questions?
Right.
What is the role of pressure, temperature, and salinity on the product of solubility?
Okay. Well, let me first answer. The first thing was about the circulation, right? Slowdown of the circulation. The second question was about the temperature record, right? How certain we are. Okay, on that one I answered, I think. The third one is effect of temperature,
pressure, and salinity on the
and pressure on KSP.
Okay, yes, but yes, on product solubility in omega.
Right. Okay.
Yes.
So that's about it, right?
Yes.
Okay, let's continue in 10 minutes or 9 minutes, okay?
Thanks.
Okay, good. I need to drink something.
Yes. Two.
Okay, Stefano, I'm ready when you are.
Okay, super, super. Okay. So now we are gonna up in the last section. Please have a seat. Thanks. Now we're talking about more ecological stuff, I guess. Always from a geochemist point of view, but it's coral reefs and climate change. Please, Jonathan, students are.
Yes, just before I start, I would like to answer some questions. So the question was, what is the effect of temperature, salinity, and pressure on the dissolution constant of calcium carbonate in the ocean? So the effects of temperature and salinity are relatively small. We can neglect them for first approximation, but the pressure has a very strong effect on dissolution for calcium carbonate. It increases the KSP, and therefore, as you press, you put high pressure, you dissolve the calcium carbonate more strongly. And that is an important effect in the deep ocean. That is why also you have this strong dependence on depth. In terms of the temperature, how we reconstruct the temperature based on the CO2, I think I talked about it, but I did not answer the question about the circulation, whether the general circulation of the ocean is slowing down because of global warming. Well, I must admit that this is not something that is directly measurable yet. but it comes from models. Lots of people like to play models, and they can calculate that as we warm up the surface ocean, then it will be more difficult to make the North Atlantic deep water, and therefore it might be that it will slow down the general circulation of the ocean. But I'll stop here and go to what we want to talk about today, and that is on coral reefs. So I don't know how many of you ever saw a coral reef or dived on coral reefs, so I decided to show you a little movie. You see it?
Yes.
Okay, so of course, everybody get excited about the fish. But of course, the more important part is really the reef itself. You see the framework of the corals, lots of fish coming and going, running away from big fish. But here you can see the corals themselves. They make a huge ecological system that is the most diverse and the most productive ecosystem in the ocean. It is extremely productive. That is so surprising because the open sea next to it is not productive. It is actually poor in nutrients and doesn't have. Sorry. So if we look at the pictures again, the most impressive part are the fish. If you can see, all the fish are facing in one direction. Also here, you know why?
Because of current.
No, yes, because of the current. But why are they facing the current? Because they eat plankton, and the current is bringing plankton. So these are all planktonivorous fish, okay? And if you actually look at the coral reef, it's basically a big filter. It's a system that filters plankton out of the water, and this is how these coral reefs are getting the nutrients. As I said, it's the most diverse and complex ecosystem in the oceans, highly productive, 50 to 100 times more than the next open ocean, multiple of symbiotic relationship of all types and sorts, and of course, between the corals and the symbiotic algae, and it is very important component of the global carbon cycle, despite their small area. Okay, the area that coral reefs occupy is very small, um, much less than 1%, but in terms of carbon, it can be up to 5% of the calcium carbonate production in the ocean. Now, of course, economically, it's very important, and I'm not going to talk about that. So we all are very impressed by the symbiosis between the corals and their symbiotic algae, as you can see here in the high magnification. And here in the fluorescent microscope, you can see it in red fluorescence, the symbiotic algae on the polyps. The amount of symbionts in coral reefs is about 1 million per centimeter square. So this is a huge concentration of algae that are all sitting within the tissue of the corals, and obviously they have a very strong function in feeding, in maintaining the energy of the corals. Often you will see the following: calcium carbonate plus 2 bicarbonates, we already talked about it, precipitate calcium carbonate and produces CO2. Now that CO2 can be taken by the symbiotic algae for photosynthesis, and therefore when you have photosynthesis, you increase the calcification. And this schematic was presented first by Tom Goro, 1959, and it is still maintained by most of the people that the symbiotic algae help in calcifying of calcium carbonate in corals. It is also well observed that in the light, they have much more calcification than in the dark, and that makes sense from this equation. But actual measurements directly, we have problems to prove this, and I will not expand on it because we don't have enough time. But again, despite the logic of it, it is not so simple. Now, as I said, coral reefs are abundant between 18 degrees north, between 30 degrees north and 30 degrees south latitude, where the temperature is above 18 degrees Celsius in the winter. So if you have colder temperatures, coral reefs are not found there. And in all the rest of the ocean, whenever you have shallow water, and within these two boundaries, you can have coral reefs. The primary productivity where the coral reefs are found is generally very, very low. As you can see here from the blue dark color, this area of the ocean is really the poorest area in the ocean where you have low productivity. And still, the coral reefs like to live in this oligotrophic water. Okay, so this is really the first paradox of coral reefs. It is like oasis in the desert because it's an oligotrophic blue ocean, and suddenly we have within the blue ocean, we have a big oasis of high productivity, high life, high diversity, and whatever you want. So around the coral reefs, the productivity is 0.1 or 0.2 grams carbon per meter square per day. And within the coral reef, the productivity is 10 to 15 grams carbon per meter square per day, up to 100 times even larger than in the surrounding seawater. So how does it work? The reason why the surrounding seawater has very low productivity is because it is in oligotrophic sea where you don't have much nutrients. The nutrient concentrations in the open water that surround the coral reefs is usually much less than 1 micromolar, both in nitrate and in phosphate. We can hardly measure it. And still the coral reef is so productive and so full of life. The question is why? Why do we have this oasis in the desert? The traditional explanation was that the high efficiency of recycling, because it is a mature ecosystem. This is what ecologists will tell you. This is written in the ecology books, but we think it's wrong. The answer is very simple, and this is very simple. The coral reefs are oases in the desert because they don't take the nutrients from the blue surrounding waters. They take the nutrients from the particulate phase, from the plankton. The coral reefs are basically huge plankton net that stands in the middle of the ocean, and the stronger is the current, the more plankton the coral community is feeding on. You saw the fish that are feeding on plankton. There are corals that are feeding on plankton. There are sponges that are feeding on plankton. There are lots of other organisms, tube worms and whatnot. All of them eat plankton, and plankton has lots of nutrients in their body. And therefore, coral reefs are big filters that stand in the middle of the ocean and get their nutrients from the particulate phase and not from the dissolved phase. So just to remind you how beautiful is the plankton, and we can, again, to show you how the structure of coral reef is like a big filter, and many, many organisms that are feeding here, including the fish themselves, okay? And of course, if you look at a single coral, you can see the polyps, you can see they are adapted to hunt zooplankton or phytoplankton. You can see they have these dermatocysts that are cells that sting the organisms that they feed on, and you can see the mouth of the corals. So the corals are hunting zooplankton and phytoplankton and digest them and get their nutrients from it. Here is the Gulf of Eilat, where we are investigating the coral reefs. And as I said, we just were surprised to see how many filter feeders are there. Here are some sponges, here are some soft corals, here are some, even the organisms on the beach are filter feeders. Here's a tube worm. Here's a tridacna, which is a filter feeder. So if you remember the Redfield equation, you take 106 molecules of carbon and you take nitrogen and you make particulate organic matter that contains lots of nitrogen and phosphorus. And when the coral digests this food, the symbionts and the algae that live in the coral reefs get plenty of nutrients just from the digestion of plankton. So this is really the trick of the plankton, the reef system. It is basically a big trap for plankton, and it gets its nutrients from the particulate phase, not the dissolved phase. Okay, good. So very good and happy ecosystem. What is happening now under global change? Okay, so first of all, the first thing that is happening is that CO2 increase leads to ocean acidification. We talked about it. Ocean acidification reduces the calcification of corals, and I will show you some evidence for it. Second thing, of course, we have eutrophication of the coastal areas, also in coral reef countries, because of human sewage and because of mariculture and other reasons that humans are polluting the nearshore environment where corals are living. And the last thing, and perhaps the most important, is really global warming, which causes coral bleaching, and this causes mass mortality of corals. And all these three reasons together really put corals into a big danger. Okay, so let's talk first about the CO2 increase. And as I said, atmospheric CO2 increase is also increasing CO2 in the sea. So this is measured in Hawaii. You can see here the CO2 concentration, and you can see that the CO2 concentration goes in parallel to the atmospheric CO2 increase. You can also see that the pH is decreasing while the CO2 is increasing. And you see that the measurement is not very easy. It's very difficult. There is a lot of noise, up and down, but at the end, that was measured starting in 1990 and continues until today. So this record continues. I think maybe I have it, yeah. So here is in Bermuda, for example, you can see the PCO2 is increasing in the water. You can see the pH is decreasing in the water. You see that omega is decreasing because of the CO2 increase and the pH decrease. Okay, good. So we talked about it. We understand that ocean acidification is lowering the pH. Lowering the pH lowers the carbonate ion concentration, which is this one. It is being lowered. The bicarbonate is increasing, but it doesn't help us. And therefore, corals potentially can be suffering from ocean acidification. So we defined omega as the calcium times the carbonate divided by the KSP. And normally, KSP in the ocean for aragonite is about 3 or 4. And therefore, you would expect it not to dissolve. But it turns out that if you take measurements, then when omega goes below 3, we already start to see dissolution on coral reefs. And I want to show you this from work that we were doing in Eilat. So this is the Gulf of Eilat, and this is our coral reef here. This is a few of our stations that we were studying. This is the underwater observatory, if anybody has been there. And we put sampling devices and CTDs in the lagoon right here and right here on the reef face and the reef flat. And we may take seawater measurements and we measure the currents. And from all that information, we get very interesting data. So here, for example, we see day and night oxygen concentrations on the reef. And you can see that during the daytime, oxygen goes up because of photosynthesis, and during the night, oxygen goes down because of respiration. And again, photosynthesis, respiration. This is the oxygen level in the open sea. This is the saturation level. And so you can see that using oxygen, we can see clear metabolism of the entire coral reef. And this was in the summer. In the winter, surprisingly, we have even more photosynthesis than respiration, probably because the temperature went down. So, hello? Hello?
Yes, we are here, Jonathan.
Okay, yeah, I had somebody talked. Okay, good. And then in parallel to the oxygen, we measure these parameters that I spent a lot of time explaining to you what it is. This is the total alkalinity, okay? So this is the total alkalinity of the open sea right here. And this is the total alkalinity in the reef in the diurnal cycle. So during the daytime, the alkalinity goes down, goes down, goes down until the evening. And then at night, the alkalinity goes back up. And again, during the daytime, the alkalinity goes down, and during the day, it comes back again. In the summer, we have big difference between the open sea and the coral reefs, and from that difference, we can calculate the rate of calcification of the coral reef. In the winter, the change is much smaller, and often we also get the situation where the alkalinity within the reef is higher than the alkalinity in the open sea. When this happens, we know that the reef is being dissolved, okay? So after many years of work, led by my PhD student, Jacob Silverman, um, we measured many times. As you can see, each point here is representing several days of work. And we were able to get the relationship between omega in the coral reef and the rate of calcification, which we call G. Okay, and as you can see, there are differences between the winter and the summer. This is the winter and this is the summer. But in the summer, we get a situation where there is a huge change in calcification from 40 to about 120 up to here. So this is all as a function of very small change in omega from 3.7 to about 4.4 or something like that. From this point to this point, factor of 300% change in the calcification due to relatively small change in omega. This is not something we expected, but this is what we are measuring in this reef that has been studied probably more than any other reef in the world, okay? And if we calculate what should be the effect of omega and effect of temperature on calcification from inorganic experiments, then we have to put it on a, here is omega, here is calcification, and this is the temperature effect. You can see the dashed line are the temperature effect. So what we have in our coral reef is a combined effect of both temperature and omega together. And that gives us this line with all these error bars. It includes also many other coral reefs in the world that had similar data, where we can compare the inorganic precipitation rates of aragonite to the coral reef measurements. And from this plot, we decided that it's enough to work only in Eilat, even though it's a very beautiful coral reef. We decided to go to Australia. In Australia, we have the big Great Barrier Reef, and you can see this is a lizard island in the northern part of the Great Barrier Reef. The coral reefs, that was in 2009, sorry. The coral reefs were still very beautiful and amazingly growing well and quickly. And we were able to measure for 2 years, in 2008 and in 2009, the diurnal cycle of calcification in the reef. And you can see here 1 year and the second year, and the results are almost identical. And what you can see here is that during the night, we had a little bit dissolution here, and during the day, a lot of calcification. And again, at night, a little bit dissolution in 2008, slightly more in 2009. I don't think it's significant, the difference between the 2 years, but it is certainly significant that at night we got almost no precipitation, and in the daytime, lots of precipitation, okay? If you plot it like that as a bar diagram, so this is 2008, this is 2009, and this is the same reef in the same location that was the work that was done by Barnes and Kinsey in the 1970s. And they measured much higher calcification during the daytime and low calcification during the night, which is kind of similar to what we measured at night. But in the daytime, their rate of calcification was almost twice as the rates that we are measuring. And we think that the only reason for that is really the increase in CO2. So if we take the same plot that we had before